Hello and welcome to another tutorial. In this tutorial, I'm going to discuss the very interesting topic of numerical integration, which has also some links to geometry, and we will explore all the different methods for doing numerical integration of real functions. Now, the main type of integration that we're going to look at is Riemann integration, and it's basically the algebraic summation of area under the function. And when we say area, we mean that the area that is basically an algebraic area, which could be either positive or negative. For example, if you look at this function, and we are integrating from a to b, so our integration interval or integral interval is let's change it to integration interval. Our integration interval is from a to b, and in this interval the function is actually crossing the x-axis, so some of one part of the function is below the x-axis and the other part is above it. So when we say the integral of f of x from a to b, we basically calculate the area under the function, between the function and the horizontal axis, and whatever that is below the horizontal axis we call it a negative area. Whatever that is above the horizontal axis we call it a positive area. And the definition of integral is the summation of all these signed areas or the algebraic area. So here is a2 because it's positive, and minus a1 because this one is negative. All right, now the definition of Riemann sum, or the definition of integral based on the Riemann sum, is that if f of x is integrable with is Riemann integrable, so if it has a Riemann summation, then the integral is defined as the limit of n goes to infinity, a summation of f of x, f the function at some xi, some point in one small interval, times delta xi. This is the length of the interval I. So if this series, right, has a limit, or basically if this series converges, we say that f of x is Riemann integrable. All right, there are other definitions of integrability, but here we're just looking at the Riemann integrability. All right, and the right hand side of this summation, basically this definition is a summation, and what it means is that we basically divide the interval into very small subintervals, and in subinterval I, subinterval number I, the length of the subinterval is delta xi, and we choose a point xi in that subinterval and then evaluate the function f in that subinterval. Okay, this is the base definition, but we can have other definitions for Riemann integration or Riemann summation as well, but this is the fundamental definition that defines the integral as a series, right? If we have a summation with infinite number of terms, it becomes a series, and the question is whether or not the series converges. And if it converges, we say that the f of x is integrable based on Riemann definition, right? So the convergence of the series. And as we discussed previously in the topic of sequences and series, the convergence of the series requires that the generating sequence, this fxi delta xi, must have a limit of 0. So the limit of fxm delta xm when m goes to infinity, when we have infinite number of very small intervals, should be 0. But the function is not equivalently 0, is not always 0. So delta xm, so the length of the intervals should go to 0, right? When we have a lot of intervals, infinite number of intervals, which makes sense, right? So this delta x is basically the length of each very small subinterval. Now the question is, how do we find the area under a given function, or how do we find the integral? And the answer is, okay, we should form this Riemann summation or Riemann series. Okay, now there are different methods to do this kind of summation. One is the rectangle estimation or rectangle method, and this pertains to mostly, just for convenience, most of the time it pertains to a uniform partitioning of the interval. So our integral interval or integration interval is from A to B, and this blue curve is our function. In terms of the forward approximation at each subinterval, first of all, it's a uniform partitioning, so the lengths of all the subintervals are the same, and if we have n subintervals, the length of each subinterval is b minus a divided by n, okay? And then the forward approximation is that at each subinterval, choose the value of the function at the starting point of subinterval, all right? So the area under the curve of f of x in each subinterval is approximated by the area of this rectangle with a leading edge right at the beginning of the function, right, for the subinterval. So the area is approximated by f of xi. Xi is the beginning, xi plus 1 is the end of the interval I, times delta x, okay? And delta x is just the length of the subinterval. Now if we do backward approximation and then at each subinterval we approximate the function with a constant function with a constant number, which is equal to the value of the function at the end of the interval, all right? And here it happens that this backward approximation actually overestimates the area under the curve, but it may not be always the case, all right? So in this case, we pick the value of f at the end of the subinterval I and multiplied by delta x. That gives us the area of this rectangle, all right? And then we take the infinite sum, or take the sum of n subintervals, and then let n go to infinity, all right? Now the other one is center or midpoint approximation, which means that again we have uniform partitioning, and in each subinterval we pick the value of the function right at the midpoint of the interval. So the midpoint of the interval is xi plus 1 over 2. So we evaluate the function at this point, right in the middle of the interval, and multiply by delta x. It gives us the area of this rectangle, all right? Now if we do this, any of these forward, backward, and center using uniform partitioning, when n goes to infinity, when we have infinite number of subintervals, all of these three ways should converge to the same number, which we define it as the integral of the function. In fact, there is a more general lemma or theorem that says that Riemann summation will converge to the same result, all right? So the same result is the key here for any arbitrary partitioning. So it doesn't matter if we do uniform partitioning or if like one interval is much smaller than the other one, it doesn't matter. It also doesn't matter what value for the function we choose in each subinterval. It could be the leading edge, the first value, the end value, or the center value. Doesn't matter. It always, if the function is integrable or Riemann integrable, the value of the series should always converge to the same number for any arbitrary partitioning, any arbitrary value for the function, or for any point inside the subinterval, okay? Now obviously this rectangle estimation or rectangle method quickly or very obviously gives us the fact that if we are integrating a constant number or a constant function, c, so f of x here is c, all right? So the constant function is just a horizontal line. So in each subinterval, the area of the rectangle is exactly the same as the area of the function, right, underneath the function with the horizontal axis. And then when we sum them up, we just get the value of the function times the length of the interval, b minus a, all right? So this is just comes out very obviously. We don't need to actually prove it. It just comes out of the definition of this rectangle approximation. Now in terms of calculating this Riemann summation, we typically end up with some series or sequences, the sum of some sequences. And there's a fundamental property which is the difference summation. So if we have a difference summation of the sequence, which means if we sum a sequence an, ak, and take the summation of the difference of the two consecutive terms, so ak plus 1 minus ak, from some index m to some index n. So be careful. So here the difference means there is only one unit difference between the indices of these two terms, ak plus 1. It has to be k plus 1 and k, okay? I mean, it also could be ak and ak minus 1, but what I'm saying here is that the difference should be exactly equal to 1. So this difference property says that if you sum the difference of the two terms of a sequence, the result is basically you take the last index of the sum, put it in the ak plus 1, it gives you an plus 1, minus you take the first index, put it in the am, all right? And it's very easy to basically prove. You just write all these terms, am plus 1 minus am plus 2 minus am plus 1, etc. And all the terms cancel, only the first term ak, am, and the last term an plus 1 remain, okay? That's why this summation of the difference of the sequence is the a at the last term, an plus 1 minus am first term, all right? Now there are some useful sequence sums. So if I take the sum from index m to n of a constant number, which could be 1, because if I calculate for 1 and then for c is just c times multiply the 1, right? It's c times the number of terms in this sequence, because we're just summing up some constant number some number of times, right? And the number of times is n minus m plus 1. And what matters here is because in the Riemann sum, eventually n goes to infinity. We have infinite numbers. So what matters is just the order of the sequence, which is n, right? If you have n terms, the order is n. If you sum from 1 to n of k, so we're summing 1 plus 2 plus 3 all the way to n. And we also could include 0. It doesn't matter. It doesn't change the result. The result is last term, which is n, times last term plus 1, which is n plus 1, divided by 2. So n here represents the last term. So if the index was from 1 to n minus 1, we should have n minus 1 times n, because n minus 1 is the last term, all right? So last term times last term plus 1 divided by 2. And when n goes to infinity, the order of this summation is n squared over 2, all right? So sum of k squared from 1 to n. So basically we are summing 1 squared plus 2 squared plus 3 squared, etc. is equal to the last term times last term plus 1 times twice the last term plus 1. So n times n plus 1 times 2n plus 1, all right? N is the last index basically. So n, last index, n plus 1, 2n plus 1 divided by 6. And when n goes to infinity, n is much greater than 1, 2n is much greater than 1. So the order is 2n squared over 6, which is, no, the order is n times 2n over 6, which is 2n cubed over 6 or n cubed over 3, all right? And similarly for summing 1 to n of k cubed, which is 1 cubed plus 2 cubed plus 3 cubed, etc., is last index plus 1 divided by 2, all of it squared, all right? And when n goes to infinity, we have n squared over 2 squared, which is n to the 4th power divided by 4. This is the order of this summation, which is the most important thing to know when we are trying to calculate the Riemann series of the integral, all right? Now, how do we actually calculate these, right? How do we find these results for k squared, k cubed, or even 1 or a constant number? What we do is we use the difference property here. And if I'm trying to find k from 1 to n or 0 to n of k to the some power p, which p is an integer, in this difference property, I set the ak or the sequence to k to the p plus 1. So I increase the power of the k by 1 unit, k to the p plus 1. So if I'm trying to find the summation from m to n of 1, So p is 0. Then here I put ak equals k. And when I calculate from m to n of k plus 1 minus k, and on the left side I have 1, so sum of 1, which is I'm looking for, and it automatically gives me the result, which is n plus 1 minus m. So n minus m plus 1, alright? So that's how we calculate the sum of 1 or a constant c. If I want to calculate the sum of k, here I put k squared. So k plus 1 squared minus k squared gives me 2k plus 1. So the sum of 2k plus 1 is 2 times sum of k plus sum of 1. And we already calculated sum of 1. So it's not only this part and using the difference, but we have to also use the recursion. So in order to calculate the sum of k, first we need to calculate sum of 1. And similarly, if I want to calculate sum of k squared, I put k cubed here, and then I have some terms which is sum of k and sum of 1. So in order to calculate sum of k squared, first I need to calculate sum of k and sum of 1. And similarly, if I want to calculate sum of k cubed, here I put k to the 4th power. And then in order to find it, I need to already know the results of k squared, sum of k, and sum of 1, which I already have it. So we use this method, this technique of difference summation and the recursion that helps us backtrack the results and find k cubed by knowing the result of k squared, k, and 1. Alright? Now, how do we use this? Let's look at an example. So let's look at the integral of a linear function, just f of x equals x, over the interval from a to b. And we're going to use the forward approximation. So area of each rectangle under the curve is f of xi, which xi is the leading edge. So the beginning of each subinterval times delta x. And it's a uniform partitioning, so delta x is just the length of interval b minus a divided by n, alright? So the Riemann definition is that integral of a to b f of x dx equals to limit of n goes to infinity of this sum, I from 0 to n minus 1 f of xi delta x. Now I prefer to use the index from 0 to n minus 1 to say that I have n intervals. Some people prefer to use from 1 to n. It doesn't matter, because when n goes to infinity, only the order of the function matters. Any term that doesn't have n doesn't really matter, alright? In terms of the fact that only orders of magnitude matters when we try to simplify the result. So if I want to find this summation, first I need to find xi, which is a, the beginning of the interval, plus I times delta. So x0 is a, right, for the first interval. x1 here is the second, is a plus delta. x2 is a plus 2 delta, etc. Which we can explicitly write it as a plus b minus a over n times I, alright? Remember, I is the variable, I is changing. So sum of 0 to n minus 1 of f of xi delta x is, we just replace f of xi by the definition of f of x, which is x. So f of xi is equal to xi, so is equal to this, and multiplied by delta x. So is a times delta b minus a over n plus I times delta squared b minus a squared over n squared times I, alright? Now remember, I is the variable, so this whole first term, a b minus a over n, is like a constant. And when we sum from 0 to n minus 1, we have n terms, so we just multiply the whole thing by n. And the n cancels out. The first term, the summation of the first term gives us a times b minus a, alright? Plus b minus a squared over n squared is a constant. It comes out of the summation, and we have to sum from 0 to n minus 1 over I. And remember the rule, the summation is last index n minus 1 times last index plus 1, which is n, divided by 2. And the n cancels out. We have a b minus a plus b minus a squared over 2 times n minus 1 over n, which is 1 minus 1 over n. So we end up with a constant term, ab minus a plus b minus a squared over 2 plus a term that depends on n, which is our error term, b minus a squared over 2 times 1 over n, which we can also write it in this way, b minus a over 2 times delta, because delta is b minus a over n. All right. Now the thing is that when we take the limit, when n goes to infinity, this error goes to 0, obviously, which means that the series actually converges. So the integral, the Riemann integral is available, or the f of x is integrable or Riemann integrable, all right? Because the error goes to 0. So the series converges. And we end up with this a b minus a plus b minus a squared over 2. If you simplify it, it becomes b squared minus a squared over 2. And the way we define this result, or the way we interpret this result, is that the integral of a to b of x dx is x squared over 2 calculated from the difference from a to b. So if the integral symbol is more like a sum, this vertical line is more like a difference. So the integral mimics a sum notation, S notation or sum. This vertical line mimics a difference notation. When we say x squared over 2 from a to b, it means take the difference of this function from a and b. So b squared over 2 minus x squared over 2. Now this function x squared over 2 has actually a name, which is called the antiderivative, and it's related to the fundamental lemma of calculus, which says that if I find a function that when I take its derivative it gives me f of x, then the integral of f of x becomes the difference of that function over the interval that I'm integrating over. So I know that the derivative of x squared over 2 is x. So the integral of x from a to b is x squared over 2 from a to b. All right? Now, just by the definition of this Riemann summation, we can easily prove two properties. One is the linearity property, which means if we integrate f plus some coefficient, some number g of x, it's equal to integral of f of x plus lambda, the coefficient, times integral of g of x. This is because this is the property of the summation, right? Sum of f plus lambda g is equal to sum of f plus lambda sum of g. And when we take the limit, it becomes integral. The other one is the breakpoint, and that means from a to b of f of x dx, we can pick any intermediate number c and break the interval of a and b to a to c and c and b. And the integral is equal to integral of from a to c and plus from c to b. Now in general, c doesn't have to be some point inside the a and b interval. It could be outside. It doesn't matter. This equality always holds. And you can easily prove the case when the c is inside the interval just by looking at this summation, because then you just have to break the index. Instead of having 0 to n minus 1, you have 0 to some m index, and from index m to n minus 1. And it gives you the summation here, all right? So this was one example that we were able to find the antiderivative of the x, which is x squared over 2. Now similarly, we can use the rectangle approximation and uniform partitioning to, for example, find the integral of x squared. Again, the same thing, xi is a plus I delta x. And then when I do the summation of f of xi delta x from 0 to n minus 1, so delta is fixed, comes out, times f of xi, which is xi squared, which is a plus I delta squared, which is a squared delta squared I squared 2 delta ai. Now here I'm not going to exactly calculate this because I already know that I'm going to take the limit of n when n goes to infinity. So I just look at the orders of each term. A squared is a constant, so when I sum it, it gives me a term n, so it's order n, all right? And delta is order 1 over n. So when these two terms multiply, it just gives me a constant number, which is a squared, times delta has a b minus a, right? So a squared b minus a. And then the second term is delta times delta squared, which is delta cubed, which is b minus a over n cubed. So it has a 1 over n cubed term. And then the summation of I squared gives me an order of n cubed over 3, right? The exact summation is this. But I don't care about the exact summation. I just want the order of magnitude, which is n cubed over 3. And delta cubed has a 1 over n cubed, so they perfectly cancel out. It gives me a b minus a cubed over 1 over 3, all right? B minus a cubed over 3. The last term is 2 delta squared times a times I, right? And the summation of the I gives me n squared over 2 as the order of magnitude. And also have a delta squared, which is 1 over n squared, proportional to 1 over n squared. So they also cancel out. This gives me a times b minus a squared. Now if you simplify this, it gives you b squared minus a b cubed. So if you simplify this, it gives you b cubed minus a cubed over 3. All right? And this means that the integral of a from a to b of x squared dx is equal to the antiderivative of x cubed over 3 from a to b. So take the difference of the antiderivative x cubed over 3 from a to b, which is you put b here, b cubed over 3 minus, and then you put a here, a cubed over 3. So we were able to find the antiderivative of x and x squared, and this gives us the exact value for the integral of these two functions. And because of the linearity, now we can find the integral of any second order polynomial, right? And so one last thing about the polynomials is that I'm going to jump ahead, but I'll come back to this again later, is that in general, we can show that the integral of a polynomial of any arbitrary order m, remember for polynomial, the m is 0, 1, 2, 3, etc., right? From a to b, polynomial has a very nice antiderivative. So x to you increment the power by 1 and divide it by the new power m plus 1. So integral of xm is xm plus 1 divided by m plus 1. And it's obvious if you're familiar with taking the differentiation or taking the derivative of this function is exactly xm. So the antiderivative of xm is xm plus 1 over m plus 1. And the definite integral, or the integral from a to b, is the difference of this antiderivative from a to b. So you put b here, b to the m plus 1 over m plus 1, and then minus, you put a here, a to the m plus 1 over m plus 1. All right? Now we can use two approaches to prove this. The first approach, just the standard definition and calculate the Riemann sum and take the limit. All right? And then the other one is use the approximating function. What do I mean by approximating function? So in approach 1, which is the standard definition, you put the integral of a and b of f of x d of x. You put it equal to limit of this summation when n goes to infinity. In the approach 2, what we do is that in each subinterval xi and xi plus 1, we approximate the function f of x with some other function. All right? And for example, in the rectangle method, we approximate it with a constant function, right? Each rectangle is basically an approximation of the function, assuming that the function is approximated by a constant function. So in general, we can write this summation in a more general way like this. And this is still a series because we're summing over all the subintervals. But in each subinterval, we can define an exact integral based on an approximating function, all right? So if we know the approximating function, or if we choose a proper or easy approximating function, we should be able to calculate this integral exactly. And then again, the general theorem is that whatever you do, this summation should converge to the value of the integral. So these two summations, the limits should give you the same result. All right? So this was an introduction to the concept of integration. In the next lecture and the next few lectures, we are going to look more into the implementing a Java code and how to write a code to actually calculate these summations and find the integration. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue the discussion on how to implement numerical integration. We're talking about one-dimensional functions at the moment in Java. So our functions are basically f of x, and we want to know how to implement those. And the method that we discussed so far was rectangle estimation based on uniform partitioning, and we said that we could have a forward approximation, backward approximation, or midpoint approximation. And in each sub-interval, we said that we can actually approximate the function, the value of the function, by a constant number. And then we did some examples. For example, f of x equals x, f of x equals x squared, and we were able to show that these functions are Riemann integrable, and we also found that we found the exact value for the integral from a to b. And then we said that this is basically related to antiderivatives of these functions and how the general or the fundamental lemma of calculus works. Now we're going to look into the numerical implementation. So first we try to do implement the rectangular estimation based on uniform partitioning, and we define first, just like what we did for root finding, we define an interface to enforce the fact that the input is a real variable and the function also returns a real function, right? So we define an interface that builds this contract with the user, with anyone who wants to use our code, all right? And we can define it as an integral function. This is the name of the interface. Or even better, we can just use the built-in function interface in basically Java library, the built-in Java library. And the way it works is that it takes two parameters, so it's a parameterized interface or parameterized class, and the first parameter is the type of the input, which we can put as double, and the second one is the type of the return, or the return type of the type of value of the function, which is also double. So we can use this, right? Any of these should work. And then we define a class that performs the summation, and obviously we should have some sort of stop criteria because we cannot sum over infinite number of terms. So it could be the number of terms. So we say that, okay, just sum over 400 terms or 200 terms. It could be the convergence. We could also implement a convergence test for the series. And if you recall, in the topic of sequences and series, we discussed this. We can implement the test based on the absolute error of the series as we add more and more terms, or we can test based on the relative error of the series, all right? Now let's head to Eclipse and try to implement these. So here in the Eclipse, I'm going to create a new project and call it the demo integral. And in the demo integral, I'm going to create an interface. Let's call it integral function. And here I'm just going to create a double value double x. So this is a function, and you recall, if we have a public interface, by default this method double value is going to be public and abstract. So these two are implicit here in the definition, public and abstract. And you already know the routine that we are going to use lambda expression most of the time. Use lambda expressions because that makes life easier, all right? Now, as I mentioned, there is also a built-in function in Java library, the function interface, but here I'm just defining an interface, and then I'm going to create a new class called integral, and in the integral, let's call this, actually let's refactor it, rename it with integral 1D, one-dimensional integral. Later we will have 2D and 3D integrals too. And here what we are going to have is we just pass a integral function. So integral function is func, and then in the constructor we're going to just pass in an integral function, function func. And because this local variable has the exact same name as our global variable or class level variable, we have to make use of this modifier to avoid any shadowing of the variable, avoid shadowing of a class variable, right? All right, now method. So method 1 is a rectangle estimation or rectangle approximation plus uniform partitioning. So we're going to say that public double get integral or integrate. For example, let's call it integrate, and double start, double end. All right. So how are we going to implement this? Is let's call this actually forward rectangle or rectangle forward. So we're going to implement the rectangle approximation based on forward summation. All right. So we create an array of doubles, double vals or f vals, or let's call this x vals. These are the beginning edge of each sub interval, new double, and the length should be endpoint. So here we're going to set the int as terms, num terms, or number of terms. Let's call these terms. How many terms should we sum? So terms, and then for int I equals 0, I less than x vals, I plus plus. What we're going to do, x vals I, actually this should be x vals dot length, is start plus I times delta. So we have to also define our delta, double delta, which is end minus start divided by terms. All right, I times delta. This is the definition. We have n terms, and after finding the x vals, what we are going to do, basically we are going to create our summation, double sum equals 0, and then we're going to again write another for loop, I equals 0, I less than x vals dot length, I plus plus. Here we just say that okay, sum plus equals delta times func dot value add x vals I. All right, so we're just calculating the summation, and eventually we return the sum. Okay, so let's go and test this. Test, we create a main method here, or maybe let's go and create the main method outside that. So new class test integral, we want to have a main method, and in the main method I'm going to create or invoke test1, and in the test1 is going to be public or private static void test1, and in test1 I'm going to define an integral function, and we could also change this to integral function 1D. I think that's a good idea. Integral function func, is equal to t goes to, for example, t. So let's first integrate a constant function, and then we define an integral 1D, integral finder, for example, which is new integral 1D, and we pass in our function, and then double result is integral finder dot forward rectangle from 0 to 2 with 100 terms. And let's make sure these are doubles, 0 to 2, 100 terms, and we're going to sys out the result. Okay, gives us 2.00, basically 2. all right, and that's correct. If I set it to 4, it should give us 4. Yes, if I set it to 2, it should give us 2 times 4, 8. Yes, and recall, basically this is testing our assumption here, or what we immediately realized based on the definition of this rectangle estimation, that for any constant function, the integral is just the value times b minus a, right? So if c is 2 and a is 0, b is 4, then we get 2 times 4, which is a. all right, now let's try some other function, but first I'm going to change the name of this interface. So refactor rename, I'm going to call it integral function 1D. okay, finish it. So in the integral we also have integral 1D, alright, and here we also have that. Now if you recall, I mentioned there is a built-in function interface, so function t1 t2 interface. So let's call it function Java util function. So t and r, which is double. The first one, t, is the input type, and the r is the return type. Func is equal to, basically t goes to 2. okay, let's call it func1. So we're using lambda expression. And here what I'm going to do, I'm going to basically have the same code here. Func1 integral finder func1 result 1, I'm going to return the result. But what I'm going to do here, I'm going to go to the integral 1D and define another constructor based on let's also remove this, based on this function interface. So function tr, I'm going to pass double func, and basically what we're going to do here, we're going to say that t goes to function dot apply t. So I'm basically doing a conversion here, but it's just because this function interface is built in, it's most likely that another person knows about this. So I'm just saying that, okay, if the user uses this one, my constructor just converts it to my integral function. It's not the cleanest way, but this type of adapters or conversions are typical in this case. all right, and we go here, integral finder 1. Let's test that this works. It does not work. Let's see why. All right, I'm going to it's calling a native method to a double. So apparently it's not able to do the conversion here. and I guess let's see if we can define this as a, so this dot find equals new integral function 1D. Let's see if we can define it as an anonymous class, and then we are going to return applied x. Let's see if this works. No, it still cannot work. Bad type on operand stack. Alright, apparently this interface doesn't work. Function double it should return a double, and okay, so if it returns the double class, we get the double value. Let's see if this works. I think the problem is with the type conversion. No, it still doesn't work. So maybe the types are different. That's a little bit strange for me, but okay, we can stick to our basic definition of integral function 1DR interface. Alright, so right now I'm just going to remove this. Maybe later on I'll try to test to see what's going on here, but this works. So our test 1 is going well, right? Now let's do test 2. In test 2 I'm going to set this to t. So, and here test 2, and I already know the so the forward approximation is equal this, and then we also do a sysout. Exact result is equal to double exact. So let's maybe do the double start is 0, double end is 4.0. Here we put a start and end. Exact is x squared over 2, so 0.5 times end minus start times start, and we put this here. So we just want to compare these. So the forward approximation here is 7.92. The exact result is 8. So the error is pretty large, and that's not good. And the way we reduce the error, we increase the number of terms. So instead of 100 terms, 100 subinterval, I'm putting 1000 subinterval, and I get 7.992. Still not good enough. Still, it's close, but it's not good enough. Now the problem with rectangle approximation is that if you look at the error, all right, the error of the rectangle approximation is proportional, linearly proportional to the delta, or the length of the subinterval. The smaller it is, the smaller the error. All right, so if I, instead of 10 subintervals, I have 100 subintervals, so increase the number of subintervals by 1 order of magnitude, I reduce the error by 1 order of magnitude. Now this is not good, because then I have to increase the number of subintervals by a very large number to get a very good error, or a very small error that I want. All right, so rectangular approximation, if I reduce delta by 1 order of magnitude, or increase the number of subintervals by 1 order of magnitude, the error goes down by 1 order of magnitude linearly. Okay, now a better way is trapezoid method. So the trapezoid method gives exact result for any first order linear function, and if you recall, the rectangle method gives exact result for a 0th order or a constant polynomial. So the first order, the trapezoid method gives exact result for a first order polynomial or any linear polynomial, any linear function. And again, we assume that it's uniform partitioning, and in each sub-interval, what we actually do is, let me just copy and paste this here. So basically what we do, if you see here, it's a linear approximation. So we take these 2 points at the beginning and end of the interval, and we connect them by a line. So we are approximating this function by a line in this interval, and we calculate the area under this line, which is the area of this trapezoid. That's why it's called a trapezoid approximation, because it's based on the area of these trapezoids. All right, and the trapezoid the area is the small base, which is f of xi, plus the larger base, which is f of xi plus 1 divided by 2 times the length of the connecting line, which is delta. All right, so this length, you average them out, you average the two and times the length of the interval. And again, this considers a linear approximation of fx, and the reason I'm putting emphasis of this linear word, because this, as you will see later, is that this is the basis of how we come up with a general method, which is called the Quadrature method for calculating or numerically calculating integrals. The foundation is here, that if we can have a method that gives us the exact result for some polynomial of some order, so order 0 and order 1, right? Rectangle is only order 0, trapezoid is order 0 and order 1, or in general any order 1. Then if we implement this kind of integration or this kind of area approximation, it turns out the trapezoid has an error which is proportional to delta squared, or 1 over n squared. Now this means that trapezoid has a smaller error compared to rectangular. So in trapezoid method, if I reduce the length of the interval by 1 order of magnitude, my error goes down by 2 orders of magnitude instead of 1. All right, and this is very desirable. Now obviously, compared to the rectangle method, we have to do more evaluations of the function. We have to evaluate the function both at the beginning and at the end of the interval. But the thing is that we already do that for the rectangle too, right? Because we have to evaluate the f at the beginning of each interval, and then the end of one interval is the beginning of the second interval. So in theory, the number of evaluations of the functions are basically the same, right? So we're gaining 1 order of magnitude better approximation or a smaller error at basically no additional cost. Okay, so that's a very good thing. And so let's head back to Eclipse and try to implement also the trapezoid method. Before that, I'm going to also implement the backward approximation. So forward rectangle, backward rectangle, and in the backward rectangle, what we're going to do, we're going to xi's are still the same. So in each sub-interval, in each interval, I'm going to calculate the function at the end. So this should be I plus 1, right? So we still have n terms, but the first term is start plus delta, not the start minus delta. And start plus delta is the end of the first interval. Start plus 2 delta is the end of the second interval. And everything else is the same. Now we can also combine these two for terms. We don't need to separate for loops. We can have just one for loop. So if I put this double before the for loop, and then also move this back here, and then I don't need this, and I really don't need to also have an array here. I just can have xval, okay, and here we just put terms, and I don't even need to have this, I just put it directly here. So this is the exact summation definition of Riemann integral. This is the exact definition of Riemann integral. Delta times the value of the function at start plus I delta. Let's copy and paste this. We put this I plus 1 here. So we're calculating the function at the end of interval. Evaluation at the end of interval. Evaluation at the beginning of the interval. Okay, so let's go back here. In test 2 we have the result. Here let's also create a backward approximation, so let's call it result backward. Instead of forward rectangle, I'm going to call backward rectangle. Okay, let's make it lowercase. Okay, so we have our integral function start to end. Let's go 100 terms, and forward approximation, forward rectangle, backward approximation, backward rectangle, and exact. And as you can see, because this linear, if I go back to the slides here, the forward approximation underestimates the area in each sub-interval, right? The area of the rectangle is smaller, maybe here. For a linear curve. For a linear curve or any curve that is increasing, the backward approximation actually overestimates the area of the under the function in each sub-interval. So the area of the rectangle is actually higher than for the backward approximation, the area of the rectangle is higher than the area under the function. So the backward approximation for this function t is overestimating the result, the exact result. Now what you can see is that this is 7.92, this is 8.08. So there is the error is 0.08, and the error is exactly the same for both forward and backward. And you can mathematically prove this, that the forward and backward basically have the same error here in this case. All right. Now the last thing we're going to do is do the midpoint approximation or center approximation. So in the center, we still have delta. We evaluate the function at the center point, which is the start point, I delta, endpoint I plus 1 delta. So we have I plus half delta. And let's go back here. So we have the forward, we have backward, and now we do center. And you probably can guess that in this case the center should have an error which is half of the forward and backward. So result center approximation. Instead of having backward, I'm going to do center rectangle. All right. So in this case, it's actually giving the exact value. So the error is practically 0. Now let's change this to t squared. 21. So the exact, and then if we do that, all right, I'm going to use another test case here. Test 3. which is t times t squared, and the exact is x cubed over 3. So we're going to have n times n times n minus start times start times start divided by 3. And here I'm going to run test 3. 21.0144, 21.654, 21.333. So the forward approximation, the error is about 0.02. to 1, and the backward approximation is the error is about 3. No, so the forward approximation, the error is maybe let's just calculate also the error. So I'm going to put here sysout forward error equals plus basically forward approximation, okay, result minus exact, and then I'm going to have backward error, which is result backward, and then I'm going to have center, result center. Minus 3.2, and minus 5 e to the negative 4. And as you can see, the center has much better performance than the others. So it's wise to always use the center approximation instead of forward or backward. And the main reason is that when we do center approximation, actually this so the center approximation, what it does is, let me just maybe zoom in each subinterval, the center approximation it doesn't overestimate, and also it doesn't underestimate, right? So what happens here is that the area under the blue curve is what we are looking for, and the center approximation has some part which is higher than the curve and some part that is lower than the curve. So there is a good chance that these two actually cancel each other out to some very good degree. So what happens is that the area of this rectangle becomes much closer to the actual area under this curve, right? So the center approximation actually has an error which is 1 order of magnitude better. So the center approximation, the error is basically delta squared. Let's call this symbol. The center approximation has a better error than the forward and the backward. All right, and so these are all the rectangle method. In the next lecture, I'm going to start with the trapezoid and other numerical ways for calculating the integral. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration and how to implement it in Java. In the past lectures, we discussed the basic idea of integration, which was the definition based on the Riemann sum. And the Riemann sum is basically partitioning the interval and then evaluating the function at some point in the interval and multiplying by the delta x, the length of the interval. And we said that as if the function is Riemann integrable, then this series must converge to a value regardless of which point you choose inside each partition. We discussed the rectangle estimation of the integral, the forward estimation, backward estimation, and the center. And we said that rectangle estimation gives the exact result for a finite number of sub-intervals. The rectangle estimation gives the exact result for constant functions. And we also said that the center approximation is generally better than the forward and backward because of the fact that if we take the center, then there are some portion of the rectangle that are outside, or that are outside the area below the curve, and there are some part that is not inside the rectangle, and these two can compensate for each other. And then we said that if we want to rigorously calculate the series, the Riemann series, basically we calculate the Riemann sum and then let the number of partitions, which is n here, goes to infinity. Then we need to be able to calculate the exact, or at least the order of magnitude of some summation from 1 to n, for example. And typically we end up with the 0th order, k to the 0th power, k to the 1 power, k to the 2nd, and k to the 3rd. And the approach that I presented was the difference sum. And the basic property is that if I take a sequence AK, right, and try to sum from m to n over the difference of two consecutive terms of this sequence, AK plus 1 minus AK. If you expand this and explicitly write it, you see that all the terms cancel out except for the last term, which is you put the last index inside the one that has k plus 1 index. You end up with an plus 1 minus the first index, which is am, right? And then we said that in order to calculate all these sums, k squared, k cubed, we use this property that if I want to calculate the k to the p power, I set the ak in the difference equation to k to the p plus 1 power. And then we use the recursion. So k to the 0 power gives me the constant summation, the sigma over constant. And if I put it here, I immediately end up with this, the constant number times n minus n plus 1, which is the order of n, right? If n goes to a very large number. And the recursion happens because for k squared, we have to use k cubed here in the difference, and k plus 1 cubed gives us some terms such as k squared, k, and constant. So we use these and then we calculate k cubed. And the general property was that the sum of k to the sum m power, or k to the p, sum of k to the p when n goes to infinity is equivalent to k to the p, k to the basically p plus 1 over p plus 1. This is the order of magnitude, all right? And then I gave some examples on how to go ahead and calculate the exact integration by using the limit of the Riemann sum. And again, we don't need to calculate the exact summation. We just, if the integral is, the function is integrable, we just need to calculate the order of magnitudes. The exact summation based on n gives us also the error term, and we discussed that. And we said that for the rectangle approximation, the error is linear, which is not good, because if I want to reduce the error by one order of magnitude, I have to actually increase the number of intervals by one order of magnitude, which is not good. And then we discussed two properties of the integral, one, and they both directly come from the summation property, the property of summing a couple of numbers. One is the linearity. So f plus lambda g is f plus lambda integral of g. So integral of f plus lambda integral of g. And that's based on the condition that both f and g have integrals in the a to b interval. And the other one that is kind of important is the breakpoint property. So I can, if the f is integrable, I can break the integral of f from a to b to the integral of f from a to c plus from c to b. And c doesn't even have to be inside the interval of a, b, right? C could be anywhere as long as these two integrals are available, all right? And that's a very important property. And in order to kind of understand it, you can just look at the case when f of x is a constant function. Then the result is f times b minus a. Here we have f c minus a plus b minus c. So when we sum b minus c plus c minus a, regardless of where c is, whether c is greater than a, less than a, whatever, b minus c plus c minus a always gives you b minus a, right? And then we also looked at the integration of polynomials x, which had an antiderivative of x squared over 2 from a to b, x squared, which was x cubed over 3. And then we said that in general, for any polynomial x to the mth power, the antiderivative is x to the m plus 1 over m plus 1 when you calculate from a to b. So polynomials are always integrable. And actually, polynomials are a very important thing, as we discuss later, that in terms of numerically estimating the value of the integral. All right. Now, the next thing that we discussed was implementing the integration in Java, and we defined a interface to define a real valued function as the integral function. And then we passed that integral function or integral function 1D, because later we will expand to 2D and 3D. We will extend to that. And then we passed this integral function object to an integral 1D. So the class that we defined that actually performs the integration is integral 1D. And then we said that, okay, we implement the rectangle or any type of numerical approximation, and our stop criteria was basically the number of sub-intervals, how many times we sum. And we could also later implement the convergence criteria instead of having a hard stop criteria in terms of the number of terms. Now, I mentioned that we can use the built-in function interface in the Java library to implement this interface. So let's quickly head to Eclipse to discuss that. I have my demo integral project here, and in the integral 1D, if you recall, we had this constructor that we passed the integral function 1D. Now here I'm passing a function which is a built-in interface in the java.util.function package, all right? And it's annotated by functional interface. So it's enforcing that this has to be a functional interface. And if we go inside this, see, it's in the runtime util function in the function package, all right? It's a functional interface. It's a parameterized, it has a type, input type, and a return type, R. So we typically use the function apply, passing the input type, and it returns the type. And we can also define the composition of two functions, and then identity function, for example. And as you can see, it's designed to be used with lambda expressions because this is a functional interface. And what I'm doing here is that I pass a function which takes an input of double and returns a double, right? But then in order to be consistent with the rest of the code, I just converted to my integral function 1D, right? So this is sort of conversion, which makes it convenient not to deal with different types of interface when I write the code. So when I'm writing all these methods, I want to deal only with one interface, which is my integral function 1D. But because most programmers might already know about this function interface in Java language, it's good to have this capability, right, for the constructor to accept that. So here I use a lambda expression to convert to this integral function 1D, which is also a functional interface. So I get this function and call the apply method. Remember, it returns a double object, right? If I pass in a double, first of all, if I'm using the property of auto boxing and auto unboxing. If you don't know what these are, you can go back and review some of my early lectures on the operator overloading. So basically the idea is that we can use the double primitive and the double object interchangeably, and the compiler is smart enough to convert them. So compiler is smart enough to handle it. And this was the basic idea of operator overloading. And this double class has a method called double value, which I'm using here. And whenever you use a double in place of a double object, the compiler can do that. Now the problem is that this function is supposed to return a primitive type, not a double object. That's why I'm calling this dot double value on the function. Otherwise you will get an error, because then the compiler says, okay, I really can't do anything about the fact that I'm returning a double object, and the double object I can't do this kind of multiplication with a double number, because there is no type conversion here. Okay, so you have to call this double value here, and then in the test integral, if you see here in test 3, I already created this. Okay, in test 1, if you see now, first I define an integral function 1D, which is a constant t goes to 1, and then I call the forward rectangular approximation to integrate it from 0 to 4. And then I'll define a function interface, double t returns a. So the thing is that if I remember, this function has to return a double object. So if I return, for example, 1 here, let's turn this to 1. This will give me an error. Actually it doesn't, it works, because it automatically does the boxing and unboxing. Now as you can see, I'm passing this function 1, which is a function interface. Now if I don't call this double value, let's see what happens. So basically here now the return type of this interface, a lambda expression, is a double object, not a double primitive. It still works. And so that's also good to have. But let's say we say 2t, for example, here. Instead of constant, we try 2t. Let's see what happens. Still works. Both of them work fine. So everything works fine here. And you can use this. Most of the times, if you're dealing with a one-dimensional real function, you can use this built-in function interface. There is also a 2D version of it, which is called the by function, but right now we're just using this function interface. All right. And then when we progress in the calculation, numerical calculation, we also talked about the trapezoid method, and we said that the idea of trapezoid method is to enhance the idea of rectangle method, rectangular approximation. And we said that, okay, in each sub-interval, instead of approximating the function with a constant function, we approximate it with a linear function, right? Consider a linear approximation of it. And that means that the trapezoid method always gives an exact result for any linear function. If my f of x is a linear function, when we approximate it with a linear function in each interval, we actually approximate it with itself, right? And then we said that then instead of summing f of xi times delta x, the area in each sub-interval is f of xi plus f of xi plus 1 over 2 delta x. And we sum over this, all right, from 0 to infinity. And this enhances the error, the order of magnitude of the error, So rectangle was a linear error, but the trapezoid was squared, second order, which is a better enhancement, which is a good enhancement. And but we didn't implement it in Java, so let's head to Java and try to implement it. So if I go to integral 1D, remember this is the class that implements all the integration. So public double trapezoid, and again double start, double end, and basically in terms, or terms is basically the number of some sub intervals. So what I'm going to do, and then yeah, obviously we have the similar things here. We define our delta, and again the idea here is that we're doing a uniform partitioning. That's the idea for now. We will see how to extend this to non-uniform partitions, because in fact non-uniform partition in most cases is a better choice. It gives us a better order of magnitude for the error. Now in each subinterval, instead of summing delta times the value of the function at the center here, I'm going to, so the first thing I'm going to do, I'm going to create an array of funcvals, new double terms. So how many times do we need to calculate the function value? So if you recall, let's say we have 1, 2, 3 subintervals, right? Our term variable is 3. Then I need to calculate at here, here. So terms plus 1, right? So terms plus 1. And then for int I equals 0, I less than terms plus 1, I plus 1 us. What I'm going to do, I'm going to funcvals I equals func dot value at basically start plus I delta. Okay, so first I evaluate the function at all the points that I need, and then here what I'm going to do to implement the trapezoid is that, okay, sum equal plus equal delta times funcvals funcvals of I plus funcvals of I plus 1 divided by 2 or multiplied by half. All right, and this is the sum, this is the trapezoid. Now why did I create an array of the values? So why did I do this first? Because if I directly call the value method in the on the function, then I'm evaluating the function at each point twice, which is not good, right? I want to evaluate the function at all the points that I need to evaluate only once, and then use those calculated values. Now if the function is a simple function, it's not a complicated one, then it doesn't make that much difference. But if the evaluation of the function has a huge cost, then it's better to do this. Then we save some overhead, right? Let me go back to the slide and show you what I mean. So if I directly call the function in my summation, then let's say in this interval I calculate the function at a and xi, and then in the next interval I calculated f at xi again. So I'm calling the value method on the f function at xi twice, which is not good, right? So that's why I'm evaluating the function only once, get all the values of the function, and then do the trapezoid estimation. So let's go back to our test cases. So we had this test 3. Now let's call it test 4. In the test 4, also I'm going to call test 4. So in the test 4, we have this t squared, and from 0 to 4, and then we call the forward approximation, backward, center. Now let's also call trapezoid. Integral finder, trapezoid, start and 100 terms, trapezoid approximation, and then let's also look at the error. Trapezoid error is result trapezoid minus exact. So forward, backward trapezoid 21.3328, and the exact is 21.333. So we have so the center approximation was 21.3328, and the trapezoid is also 21.3328. So as we can see, the center approximation and the trapezoid approximation give basically the same error. Okay, and that's because they have the same order of magnitude error. Now let's go to t cubed, and then the exact, I have to multiply this, the exact becomes n to the 4th power minus star to the 4th power divided by 4. So center approximation 63.9968, the trapezoid approximation 63.9968. And you might wonder why these two are always giving us the pretty much the same result. That's because when you have so many terms, a linear approximation is a good approximation of this type of polynomials. And the exact result here is 64. So the forward and backward have a large error, but the center and trapezoid are pretty accurate. And the center is more efficient in terms that in terms of the fact that we're only calculating the values of the function once. But using the trick that we use for the trapezoid, and the fact that, okay, we're also calculating the values of the function only once, then these two are basically, in this case, they have almost exactly the same performance in terms of the evaluations of the function. So my recommendation is to always go with the trapezoid. All right. Okay, so this is a trapezoid, and maybe let's try to test other functions. For example, t sine of t, and we don't have any closed form exact result, so let's just compare them. Why do we have error? Okay, so we have to call math.sine. Forward 1.9178, 1.7967, and center and trapezoid, as you can see, they're giving us exactly the same result. Okay, but again, to reiterate, the main difference here is that for the center rectangular approximation, we evaluate the function at the center of each subinterval, right? For trapezoid, we evaluate the average of the function, basically at the beginning and the end of the interval, and we calculate the average and then multiply it by delta x. All right, and both have the delta squared error, the quadratic error, which is good, gives us a faster convergence. I think I made them. Okay, yes. So I was looking at the, yes. So sorry, that's my mistake. I'm looking at the, I was looking at the result center also for trapezoid. So let's run this one more time. And then maybe let's go back to t squared and try to look at the, or maybe t cubed, because we already have it. So we have result for the forward, result backward, result center, and result trapezoid. So trapezoid, now we see that the trapezoid has actually, yeah, pretty much the same error as the, it's not that much different in terms of order of magnitude. So trapezoid and the center are relatively accurate. So let's go back to t squared. End cubed or minus start cubed over 3 is the exact result. And in this case, exact is 21.333. And then both of the center and the trapezoid gives us, yeah, both of them give us very accurate results. All right. But my recommendation is to try to always use trapezoid instead of center. All right, so the next thing is that as you can probably see, we have been following a pattern, and the pattern was that we tried to approximate the function in each subinterval with a polynomial, right? The rectangle was a constant polynomial, which is basically just a number, constant number. So it's a 0th degree polynomial. The trapezoid was a 1st degree polynomial, right? Now it is just intuitive to try to basically go on with this approach. So Simpson's method is basically saying that, okay, in each subinterval, approximate the function with a 2nd degree polynomial or a quadratic polynomial. Now the question is, why would this work? And the reason is Taylor series. And we briefly discussed Taylor series when we discussed polynomials. So the idea of Taylor series is that if we have a function that is very well behaved, it doesn't have a crazy infinite discontinuity or something, and that's pretty much the condition for Riemann integrable. So the function, if the function is continuous and it has integral, then we should be able to expand, do the Taylor expansion, right? The idea here is that if the interval is, the subinterval is small enough, we can expand the function as a Taylor series, right? A Taylor polynomial. And as we increase the order of that Taylor expansion, the degree of that polynomial, better and better we approximate the function. And then I mentioned this idea that, okay, if the interval is small enough, and if I come up with an approximation, f sub approximation for the function, then these two integrals should be pretty close enough, right? We can, instead of directly calculating the integral of the function in a small interval, we calculate the integral of the approximating function, the f of approximation, right? F sub approximation. But the key here is that we choose this approximating function wisely, in a clever way, so that we can actually calculate exactly this integral. And which is the function that always has an exact integral is a polynomial. No matter what these coefficients are, we can always exactly calculate the integral from a to b, right? That's why we like polynomial and use polynomials to implement the rectangle, trapezoid, Simpsons, or whatever. So if I consider this approximating function as a Taylor expansion, quadratic, in each subinterval, let's say it's just one interval a and b, and it's very small. Then if I approximate the function with a quadratic polynomial and put it in the integral, I get this. So if the integral if the interval ab is small enough, so that this approximation with a quadratic polynomial is accurate enough. Then the integral is approximately b minus a, which is the length of the interval, over 6 times f of a, so the value of the function at the beginning of the interval, plus 4f of m. M refers to the midpoint of the interval, which is a plus b over 2, plus f of b, the value of the function at the endpoint. And you can see the error is delta to the 4th power. So we jumped from trapezoid, which was delta squared, to delta 4th, which is a huge enhancement, right? But the price that we are paying is that we need to evaluate the function at 3 points in each sub-interval. So if I have n sub-intervals, if I have n partitions, then I have n evaluations for the function at the beginning of end of each point, also n other evaluations at the midpoint of each interval. So the number of evaluations doubles. So that's the price that I'm paying. But the order of error goes by a factor of 4. The order of magnitude is 2 orders of magnitude higher than the trapezoid. So if the evaluation of the function doesn't have much cost, it's easy to evaluate it, it's better to go with Simpson because it gives us much faster convergence on small error. But if evaluating of the function gives us higher cost, numerical cost, then it's better to stick with trapezoid and go with the trapezoid, right? Because the order of magnitude error is smaller, but we might get a faster performance because the number of evaluations is less. All right. So this is the basic of Simpson's method. In the next lecture, I'm going to implement this in Java. Thank you for watching, and I'll see you in the next video. Hello and welcome to another tutorial. In this tutorial, I'm going to continue our discussion on numerical integration with the Simpson's method. And we said that in Simpson's method, we just interpolate the function with a quadratic polynomial, and then in each interval, small interval, we, instead of integrating the function, we integrate the quadratic polynomial, which we know very well how to exactly calculate that. And it eventually gives us this result, right? And the question is, how do we actually find this integrating polynomial, or the approximation, this quadratic polynomial in each sub-interval? Typically what we do, we use a Lagrange interpolating polynomial, and we briefly discussed this Lagrange method when I was talking about root finding algorithms using Brent's method, because the idea was the same there. We had to do a quadratic interpolation and find the root of that interpolating polynomial. So the way we write down the Lagrange interpolating polynomial is that, first of all, this interpolating polynomial is unique. And you can easily prove that the uniqueness of this polynomial that interpolates the function is unique. So for a quadratic polynomial, we need 3 terms to be able to uniquely interpolate the function. And then the way we write it down is like this. It has for here we have 3 points, right? A, f of a, b, f of b, and m, f of m, which m is the midpoint. And then we know that at a, the polynomial should also go through f of a. At b, the polynomial should return f of b. At m, it should return f of m. So we write this down. We say that, okay, p of x must give me f of a, f of m, and f of b. And then I multiply each of these terms by a second degree polynomial. And that polynomial should return 1 whenever I plug in a. So x minus m, x minus b multiplied by f of a. But then I plug a into x and divide this polynomial by the result. So x minus m, x minus b divided by a minus m, a minus b times f of a. So if I want to find the coefficient of f of m, I take the two other points a and b and write down a quadratic polynomial x minus a x minus b times f of m, and then I plug m into this polynomial m minus a m minus b. So this whole polynomial returns 1 whenever I plug m inside. Now the key here is that whenever these three polynomials, these three quadratic polynomials are chosen, are written such that whenever you put, for example, in the first one, you put a here, the other two terms are 0 because they have x minus a. Similarly for m, so if I put m here, it returns 1 and the polynomial is f of m, but the other two terms are 0 because they have x minus m. Alright, so lastly, if I want to write the term for f of b, I multiply it by x minus a x minus m, and then I plug back b in this polynomial and divide it by b minus a b minus m. Alright, so this is how we write a Lagrange polynomial based on the values of the points and the values of the function at those points. Alright, so let's head to Eclipse and try to implement this Simpson's method. And we're not going to calculate the Lagrange polynomial first because we already know the result. So if in a small interval AB with a midpoint m, which is a plus b over 2, if you write down this polynomial, which looks a bit scary, but it's pretty simple, and then you plug it back here in the integral of a and b, and integrate term by term and find the exact result. The exact result is this, b minus a over 6, so the length of interval over 6 times f of a for f of m plus f of b. Alright, so in each sub-interval we have this. And now if we have n partitions, if you sum this up over all the partitions, there is also a general rule, because some of the terms, two neighboring intervals share some terms, right? So if I want to go from a to b and b to c, these two intervals share the point b, so f of b repeats itself, right? So I get b minus a over 6 f of a for f of m1 plus f of b plus the same thing f of b, and then I get a factor of 2 here. Okay, but for simplicity we just find the value of the approximation in each subinterval and then sum it up. So let's head to Eclipse. In our demo integral project we have integral 1D, and here I'm going to create public double Simpson, double start, double end, and int terms. And here again we are going to use a uniform partitioning, and we're going to calculate the values of the function, and eventually we're going to return the sum. But not only we need the values of the function, we also need the values of the midpoint, right? So let's create another array, func vals midpoint, new double. So if I have n subintervals, I have to calculate the midpoints n times. So here the length is terms, right? So the func vals are the values of the function, func vals midpoint at I, and then basically I'm going to evaluate the function value start plus I plus 0.5 times delta. All right, now obviously we don't want to go out of the index, so we want to make sure that the I is less than terms. If I is less than terms, we do this, and that gives us okay. And then now that I have this, I will create another for loop, and in each interval I have my delta divided by 6 times func vals at the beginning plus so let's remove these two. I'm going to have 4 func vals midpoint at I plus func vals at I plus 1. All right. Okay. And this should be the Simpson's method, and again we're using uniform partitioning. So let's go and test it. In test 4 we have this t times t squared, and we have the trapezoid, and now we're going to add Simpson. So result Simpson, and I'm going to call the Simpson method with 100 points. So let's see, and we can also let's just comment the errors. So we have forward, we have backward, we have center, we have trapezoid. The last one is Simpson. And as you can see, Simpson pretty much gives the exact result, and it should, because the function because it should give exact result for any quadratic function, and we are integrating a t squared, a polynomial, a quadratic function. So the Simpson should be exact. And let's go t cubed, for example, and the exact is n to the 4th power minus star to the 4th power divided by 4. So we have Simpson, pretty much exact result. Trapezoid and center are also good enough, the approximation are good, but Simpson is the order of magnitude for the error is way smaller or way better than the trapezoid and center. So it pretty much gives the exact result. So let's go T5 or T4, T cubed or T4, for example. So I have to multiply this by n, start divided by 5. And again, as you can see, center and trapezoid, the accuracy is not good enough, but Simpson is pretty much accurate. 204.8000, so 7-8 digits of accuracy. All right, so that's the idea of Simpson. And but the next thing here is that if you recall, when we were looking at the root finding algorithm, I used recursive a lot in terms of solving the problem, and the general idea is that we can use recursion to also do integration. How do we do that? So basically the point of recursion is that whenever we can divide a problem into two smaller similar problems, then we can use recursion, right? And this recursion helps us to do implicit integration. And if you recall, I mentioned that the problem with recursion is that then the JVM, the Java Virtual Machine, creates a method stack, and it's a stack tree. We go each time we call a method at one step of recursion, we create a new stack, right? So we have a stack frame, and the stack frame keeps track of the calling methods, right? So when we have recursion, we go deeper and deeper into the stack, and then we have to come back up when we get to the stop criteria, stop condition. And the problem is that this going in deep into the stack frame and coming back may not be very efficient, may not be the most efficient way. But recursion is typically typically much simpler to implement when compared to a direct approach. And then the idea of recursion or recursively calculating an integration is based on the breakpoint rule. So if I want to calculate integral of f of x from a to b, I can choose a point inside the interval and then go from A to C and C to B. So I can divide one problem into two smaller problems, okay? So the stop condition is that, again, we can use any of the methods that we chose so far. One is, for example, I can set the stop condition is that when the interval is very small, I can approximate the integral by a constant value, which is the value of the function at midpoint times the length of the interval. If or I can approximate the integral with a linear approximation, which ends up being the trapezoid method, or I can choose the quadratic approximation, which ends up being the Simpson method. All right, so I'm going to show you how to do this in Java. So let's head to Eclipse and try to do the recursively calculating the integral. So public static public double forward rectangle recursive double start double end, but I'm not going to specify the number of terms. We can do that. We can basically do that as well, but let's set the stop criteria to something else. So what are we going to do? Let's do this. Basically we don't need any of these, so what we need is a stop condition and then the return condition. And in the return I'm going to choose the, let's call the midpoint, double mid point is basically start plus end times half. All right, and then we're going to return okay, maybe we put this here. Return we are going to break it down into two smaller intervals. So forward rectangle recursive start midpoint plus forward recursive midpoint times end from to end, right? So we are breaking the integral into two smaller breaking into two smaller integrals. And the stop condition here is that if let's say math.abs end minus start is less than 1 e negative 9, for example, what we are going to do is we're going to return actually there's no point in calling it forward, right? We could call it forward, and then here we do the forward approximation func.value at the start. This is the forward approximation. Okay, now let's head to the test integral class and let's see if this works. Result forward recursive. I'm going to call the forward recursive, but we don't have any integer number of steps. And then let's call this here. All right, let's run test 4. As you can see, it's still running to do the recursion, and that's not good because it takes a lot of time to do the recursion. Let's maybe let's reduce this to 1 e negative 4. And okay, so what we forgot here is to multiply it by basically the delta x, right, times end minus start. Okay, so the recursion is stopped, and the forward approximation was 199.714. The forward recursive is 204.79218, which is much closer to 204.8. And that's because here we specified the number of terms, but we didn't have any idea of how the error changes with this. But here for the recursive, we set the absolute error, so we are confident that we should be at least 4 digits of accuracy. Let's set it to E5. Now we should have 5 digits of accuracy, right? And we can go E6, for example. $799, this is 6 digits of accuracy, okay, and still fast enough. Now similarly, we can implement the backward approximation recursively, so backward. And again, so the good thing about recursion is that you really don't need to do anything. You just break it into 2 smaller problems and call the same method. The downside is the fact that it's most likely not less efficient than if you actually implement the direct approximation, okay? So in the backward recursion, we just evaluate the function at the endpoint, and we call the backward recursion method. All right, so result forward recursion, and then we have result backward recursion, forward, backward. Let's update these with backward and run it. Now in this case, they both have the same accuracy, 6 digits of accuracy. All right, and let's do the center approximation. So backward, center, rectangle, recursive. Here we do the evaluate the function at the center, point times so actually I can put this the midpoint in the beginning, and then I just evaluate the function at the midpoint, all right, times end minus start. So here let's do the center recursive, result center recursive, backward we're going with center, okay, and then result center recursive. Okay, let's run it. It's not that much different from the backward approximation. Okay, that's because I forgot to update this with the center. Yeah. So remember, when we're doing the forward recursive, we have to call the forward recursive. When we're doing the backward, we have to call the backward. When we're doing the center, we should call the center recursive. And now we have almost the exact result. So the accuracy of the center recursive is pretty good. But I guess because the order of magnitude error is less, maybe we can just reduce the number of iterations. Yeah, it's still pretty good. 204,799. Now the problem here is that the absolute error is typically not a good idea to implement, so we can also add some relative errors. So math.abs of end minus start divided by math let me just less than 1 e negative 5, or now if the end value is 0, we can also do a star, right? So we also look at the relative error, and it still works. Okay, so forward recursive, backward recursive, and again it's better to have these relative errors as the stop criteria as well. Forward, backward, and then the stop. So we can increase this. Let's set this to 7. So I'm just increasing the relative error to make it more accurate. Okay, and now let's go to do the trapezoid, public double trapezoid recursive, double start, double end. And actually we could here give the double error tolerance. All right, we could specify that here, and then the same thing here. So we have the midpoint, and then our stop condition here is that let's set these to tolerance. So the idea is that you can actually let the user choose the tolerance, or we can just set it. It's better not to hard code the tolerance here and have the user. So for example, but for now, just for simplicity, I'm hard coding the absolute error and the relative errors. But it's better to have them as argument: absolute tolerance and relative tolerance for the interval. Okay. All right, so in the trapezoid, we find the value of the function at the start point plus value of the function at the end point, and divided by 2 times the length of the interval. So when our interval is small enough, so we just return this value. Okay, so it doesn't have a forward or backward or anything. We just take the average. The trapezoid is just one interval, and it automatically expands itself on the entire interval because of the recursion. All right, so let's go here and then do the trapezoid recursion. Trapezoid recursive, boom. Here, and here is trapezoid recursive, start, end. Let's run this. It gives the pretty much exact result. All right, and we see that the center result and the trapezoid results are pretty much the same accuracy, which is pretty good, and they're very close to the exact result. And let's try to change the function to something more interesting. Let's say math.sin of t. As you can see, the direct integration is, we can really see that the direct integration is faster than the recursion, right? And but what we see that is Simpson returns 1.857779 for direct integration. The rest, forward and backward, they're way off from Simpson. Center is 1.85799, so 3 digits, 3 decimal places accuracy. And trapezoid is 1.8573, and all of these because for 100 subintervals, right? Now instead of having the number of subintervals, if we go with the recursion and absolute error, then what we get is 1.8577. So we have this accuracy very similar to Simpson's method. The backward is the same. The center recursive is also the same. 199. So this gives the trapezoid recursive gives almost exactly the same result as Simpson. But again, Simpson with just 100 subintervals is pretty fast. So it's better. The recommendation here is to use Simpson direct integration. It's very simple. It doesn't have any overhead due to the recursion and calling methods or going into the stack method. And let's finally go and implement Simpson recursion. So public double Simpson recursive double start double end, and again the same situation here. We have the midpoint, and if the stop criteria is not met, we go with the call the same method on the start to midpoint and midpoint to end. And when the stop criteria is met, basically what we are going to do is we are going to apply the Simpson's rule in the interval. So the Simpson's rule is n minus start over 6 times the value of the function at the start, the value of the function at end, 4 times the value of the function at the midpoint. Alright, so this is Simpson. And let's also add the Simpson here. Recursive, trapezoid recursive, Simpson recursive. And Simpson approximation, non-recursive is 1.857777199. The recursive Simpson is 1.85777. So again, pretty accurate, 1988. And let's also do a benchmarking on which one of these two is more faster. So we're going to call test 5. And in the benchmarking, I just try to find a so let's find the time that it takes to evaluate the integrals. So we're using 100 subintervals here, and I'm going to use the timer method from the from my mathlib library. So I'm going to add a dependency on the mathlib, and then here I'm going to call timer. Actually we need to import it from mathutil. Timer1 new timer, and timer1 start, and then after ending this timer1 stop and timer1 dot show. Okay, and then the same thing here for the recursive. I'm going to use timer2, create timer2 start, and after doing the calculation, stop timer2, show timer2. So the Simpson duration was pretty much nothing. So it was quite fast with 100 subintervals, and it gives us very good accuracy. But the recursion, as I mentioned, takes time because of going into the method stack and recursive calling of methods. Let's increase this to 500 points, 500 subintervals. Pretty much doesn't take any time. So my recommendation is to avoid recursive implementations and always try to do direct implementation for numerical integration. Even if let's see what happens if I increase to 5,000, 2 milliseconds, pretty fast. Let's put this in the beginning. As you can see, the order of execution doesn't really matter. The direct Simpson is still very fast, extremely fast, doesn't take much time, and it gives us very accurate result. So avoid recursion whenever you can for numerical integration, okay? Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration in Java. So far we looked at the simple methods such as rectangle approximation, trapezoid, Simpson, and we also looked at how to implement them recursively. Now let's go and continue to more advanced concepts in numerical integration and advanced methods. One of them is Newton-Cotes method. And what do we mean by that? So sometimes we only know the values of the function at some given points, which are normally uniformly distributed over an interval, okay? This means that we don't have the expression of the function, but we have the values of the function that at some equally spaced points. Now, when does this happen? One use case or one case that this happens is, let's say you have a signal coming into your electrical circuit, and then you sample it at some rate, let's say 10 kilohertz, 20 kilohertz. It means every 10 millisecond or every 1 millisecond you're taking a sample of the signal, which means you're taking a value of the function, right? And sampling is normally a uniform thing, so the distance or the time between two sampling points is equal. It's always the same, it's constant. That's why you have a signal, you have the values of the signal at some points that are equally spaced over time. Now let's say you have sampled the signal, now you want to integrate it. So how do you do that? One approach is Newton-Cotes, and it says, okay, remember the Simpson's method, what we did in each small interval? Now extend that to the entire interval, right? So instead of interpolating the function in a small interval with a quadratic polynomial, what you're going to do is just interpolate the function based on the number of points that you have and a quadratic polynomial of that degree. So if I have n intervals, which mean I have, so if I have n intervals, it means I have n plus 1 points of the function, right? And that gives me n plus 1 degrees of freedom. Therefore, I can fit those points to a polynomial of degree n, okay, for polynomial, because a polynomial of degree n has n plus 1 coefficients, which are unknown, and we know them after doing the fitting. And how do we find these polynomials? These are exactly the Lagrange polynomials, which we discussed here in Simpson's method. So Newton-Cotes says, okay, try to interpolate the function using a polynomial of degree n based on the endpoints that you have. It's Lagrange polynomial. And this Lagrange polynomial in each for each, so basically Lagrange polynomial is the sum of the values of the function times the Lagrange term, right? So the whole summation is called the Lagrange polynomial, but then each term here, Li, is a Lagrange, let's call it Lagrange term, for example. So the whole summation is the Lagrange polynomial, because each one of these Li's has this property that if I plug in xi, so Li of xi is 1, Li of xj, which j is not equal to 1, is not equal to I, is 0. So Li of xj is 0, Li of xi is 1, right? So okay, and then we said that okay, now if this function is approximating my actual function, then the integration is also an approximation. And then because LIs are polynomials, we know exactly how to calculate them. Therefore, what we end up, and if you see in this summation that fxi is a number, integral of Li is also a number. All right. So our integration of f of x over a and b becomes a summation of some wi's, which we call them Newton Cotes weights. So this is the constant of weights, times f of xi, the value of the function at xi. Now, in the original definition of Simpson's of Riemann summation, we had f of xi times delta x. So we were evaluating the value of the function at some point inside in each interval, and then multiplying it by the length of the interval. Now, the difference here is that we calculate the value of the function times some weights, which are called Newton Cotes weights, right? And then these weights are the integral of the Lagrange terms, right? And this gives a better approximation of the function, of the integration, instead of having just simply f of xi times delta x. All right. Now, if let's just assume that we want to integrate over a and b, right? So if I use only 2 points a and b, I end up with so if I use only 1 point, the degree of polynomial is 0, which means I'm interpolating with a constant polynomial, and that constant polynomial is basically 1, right? It's basically 1, and therefore what we end up with, so actually the constant polynomial is 1, and then we end up with the rectangle method. So if we use 2 points, the start point and end point, a f of a, b f of b, so what happens is that we end up with the trapezoid rule. If we use 3 points, we end up with Simpson's rule. If we use again 3 points, if we use basically, so trapezoid is first degree, Simpson is second degree, and then Simpson's 3/8 rule is also the degree 3, and then we have also Boole's rule, which is an interpolation with a 4th order polynomial. All right, and this approximation is accurate when the interval is small. If the interval is large, what we do, we use the fact that okay, over each small interval I can do this approximation and then sum them up to get the value of the function, right? The value of the integral of the function. And so we can make this as accurate as we want by increasing the degree of the polynomial. And again, this whole pertains to a uniform partitioning. All right, so this whole idea of Newton Cotes rule and the trapezoid, Simpson rules, Boole's rule, all of these that are derived from this Newton Cotes rule are for uniform partitioning. Now the question is uniform partitioning is actually the optimal case? And the answer is no, uniform partitioning is not the case. And that leads us to the next and the widely used method called Gaussian quadrature or Gauss-Quadrature method. All right, and the idea is that we want to generalize numerical approximation of an integral. So far we saw that the simple definition of integral is the Riemann sum, which is the value the sum of the f of xi times delta x. And then we see that the recurring theme in making the numerical integration more and more accurate through different methods was that we started with the definition of the sum, Riemann sum, which is basically based on the fact that it approximates the function with a constant polynomial of degree 0 in each subinterval. The problem was that the error was order delta, so I need to have a lot of subintervals. And then if we want to improve the accuracy, we said that we can go to trapezoid, and it's based on the interpolating of the function by linear polynomial degree 1. It gives us an error of delta squared, and gives the exact result for first degree polynomials. And the Simpson idea was we wanted to have exact result for the second degree polynomials in each subinterval, and of course in the entire interval. And the error improved to delta 4. All right. And then the Newton codes was, okay, I can generalize all these ideas with Newton codes for uniform partitioning. Remember, those were for uniform partitioning so far. And then we saw that, okay, I don't need to actually use uniform partitioning for these ideas, rectangle, trapezoid, Simpson, right? Because regardless of how the partitions are made, I can do this kind of interpolation in each subinterval. Now what we are going to say is that let's forget about uniform partitioning. What I want is I want to be able to write this integral f of x dx from a to b as a summation. If I have n partitions, I from 1 to n or 0 to n or 0 to n minus 1 of the values of the function at some points times some weight coefficients, which are called Gaussian quadrature weights, and the xi's are Gaussian quadrature points. All right. So I want to pretty much be able to approximate the integral in this form, and we already saw that in Newton codes we can use uniform partitioning and do this kind of this thing, right? This kind of writing. But let's generalize it. Is that okay? We looked at the zeroth order, first degree and second degree polynomials. If I want to choose this and I don't want to have any uniform partitioning or anything, I have 2n unknowns, right? If I have n terms in this summation, I have n w's and n x, which I have to find. So 2n unknown parameters here, all right? And let's set the condition is that I want this approximation, this approach, to be exact for polynomials of degree 0 to degree 2n minus 1. So I want this approximation to actually give me the exact result for 2n polynomials. And if I set this approximation to equality by plugging in the x to the 0, x to the 1, x to the 2 on these terms, I end up with 2n equations with 2n unknowns. So I should be able to uniquely determine wi's and xi's. All right. Now, why is this a good way of doing the approximation of any function? Because of Taylor expansion, right? And that was the whole idea between all these trapezoid, rectangle, and Simpson method, right? So the whole idea is, okay, I want to be able to write the integral in this way, in this fashion, with some weights and some points. And then the Gauss-Legendre quadrature rule. So this was the general definition of the quadrature rule, right? Or the Gauss quadrature. This is a general definition. For Gauss-Legendre quadrature, we have the constraint that the integral should be accurate for all these 2n polynomials over the interval of -1 to 1. So that's because Legendre polynomials, which we will see later, only are defined from -1 to 1. All right. So the Gauss-Legendre rule is that, okay, this integral should be accurate for intervals of -1 to 1. And then what if I want to actually calculate the integral from a to b? We can use a linear mapping from -1 to 1 to any interval a and b. So if x is in the -1 to 1 interval, I can map it to any point in the a b using a uniform mapping, b minus a over 2 times x plus b plus a over 2. So if I put x to -1 here, it gives me the start point. which is A. If I put 1 here, it gives me the endpoint, which is B. And it's a one-to-one linear mapping or uniform mapping, and the integral of A and B f of x dx becomes B minus A over 2 integral to minus 1 to 1 f of this whole thing dx. And this whole thing can be viewed as a so this whole f of something can be viewed as a g of x function, right? So basically integral of minus 1 to 1 g of x dx, and g of x is just f of b minus a over 2x plus b plus a over 2. Okay, so if I'm able to integrate any function from minus 1 to 1, and I'm able to approximate it with some weights and points which I need to find, then I can calculate or approximate the integral from over any interval a to b. I can first transform f into g using this mapping and then find the integral of g over minus 1 to 1 and then multiply it by b minus a over 2. Alright, this gives me this approximation based on the Gauss-Legendre quadrature rule, right? And then now the question is, first of all, in order to do this, we have to find wi's and xi's, right? And the way we find it, again, we form a 2n equations, a set of 2n equations based on the condition is that we need to get the exact result. This approximation must yield in exact equality for polynomials x0, x1, x2 to x to 2n minus 1. So 2n polynomials from degree 0 to degree 2n minus 1. And it gives us 2n equations, which helps us to uniquely determine the wi's and xi's. But the problem here is that these are nonlinear equations. Because the values, the parameters or the variables are w and x. So it's not easy to solve it, but luckily it's actually possible to solve it and get the closed form relations for the w and x. And the way it happens is that with the notion that the fact that we choose minus 1 to 1 to be able to establish this equality is very good, because then every odd degree, x1, x3, x5, etc., automatically results in 0 for a minus 1 to 1 integration, right? Because it's an odd function and the interval is symmetric, so it definitely results in 0. And that helps us to be able to solve the equations in a closed form way. And the final result is this. The weight coefficients are 2 over 1 minus xi squared times p prime of order n xi squared. And p of n is the nth order polynomial, Legendre polynomial, alright? And these polynomials are defined over the minus 1 to 1 interval. So wi, we are able to find wi's in terms of the xi's. And how do we find xi's? Xi's are actually, the xi is actually the ith root of Pn, and which is the nth order Legendre polynomial. And the thing is that wi is equal to this expression as long as we do this normalization over for the Legendre polynomial. And the normalization is that the nth degree Legendre at x equal 1 should be 1. This is the normalization. When we do this normalization, wi is equal to this term, 2 over 1 minus xi squared p prime n xi squared. So we have to find the Legendre polynomial, normalize it. And when we normalize it, then what happens here is that the xi is the ith root of the Pn. Actually, the xi doesn't depend on this normalization. Xi's are always the ith roots of the Legendre polynomials, and the weights are calculated based on the xi's. Okay? And in order to be able to find WIs based on this expression, we have to normalize the Legendre polynomial. Now this table is from Wikipedia, and this shows us based on the number of points or the partitions that we choose. Let's say if I want to only 1 point, then the point, the xi is 0. The approximate value of xi is also 0. And the weight is 2. And that's because when n is 1, we are basically approximating this with a constant function. And the value of the function is obviously, logically, it should be at the middle of the interval, which is 0. And if we're setting the constant approximation, wi should be the length of the interval, which is 1 minus minus 1, which is 2. So with one point approximation, we end up with 2 times f of 0, the midpoint. That's why when the degree is 1, the Gauss-Legendre quadrature is just 0 for the center, 2 for the weight, all right? But if we have 2 endpoints, 2 points, x1 and x2, for example, then we have to use 3 polynomials, 1x, x squared. And it's actually an easy case to write it down, write the 3 equations, and write the 4 equations, right? x0, x1, x2, and x3. We have 4 equations, and it's possible to calculate the exact solutions by hand, just using the math, right? Solving the 4 equations. And you end up with the fact that the xi, x1, and x2 are plus minus 1 over square root of 3. And wi's are 1, the weights are 1. So if I want to approximate this function, this integral with 2 points, I have 1 times f, the value of the function at 1 over square root of 3, plus 1 times the value of the function at minus 1 over square root of 3, all right? And etc. If n is 3, we have the roots of the 3rd degree Legendre polynomial, and the weights are calculated from these 4, 5. All right. And then the next thing is that we can just use this table and go ahead and implement it in Java. Let's say instead of doing this for the entire interval, if the interval is large, we divide it into sub-intervals, and in each sub-interval I calculate the for example this integral using this mapping, right? So the first thing I need to do, I need to create this mapping. So let's go here to the Eclipse, and in the integral 1D, what I'm going to do here, I create a private method, Gauss-Legendre mapping double x. So the mapping is that what happens here is that whenever I do this mapping, let's call it interval mapping, and here it returns that let's say double start, double n, double x. It returns that end minus start over 2 times x plus n plus start over 2. Okay, so this maps from minus 1 to 1 to any interval start end. Okay, now we obviously we can do the reverse of this, private double Gauss-Legendre inverse interval mapping, and double start, double end, and double x. And here we do return. Basically what happens here is that we have 2 divided by end minus start times x minus end plus start over 2.0. All right. So if I set the x to end, I have end minus start over 2 times this, it returns 1. If I set the x to the start point, I get minus end minus start over 2 times this, which is minus 1. So this basically what happens here, this does the mapping from start end to minus 1 and 1. All right. And then let's do a private double Gauss-Legendre function mapping, double start, double end, double x. So what we want to do, we want to map the function from start to end interval to the return t goes to, so we want to return an integral function 1D, but what we want is to map it to the -1 to 1 interval. So we get the func dot value Alright, so let's call this integral 1D, and then the return type is func dot value functional integral function 1D. Alright, and then here we map x to so Gauss-Legendre, this should be Gauss. So Gauss-Legendre interval inverse interval mapping start end. All right, and let's remove this and t. Okay, so basically what happens here is that we create a function, so t is between so t is in start end, okay, interval, and then we use the inverse interval mapping to map it to -1 to 1 and create an integral function 1D, an functional interface that represents our basically, if I go back here, our g of x here. All right, it's our g of x. So g of x is the value of f at this point. And then what we do here, we calculate the integral of this at -1 to 1, so private basically double Gauss-Legendre, let's call this -1 to 1 interval double start double end. So if I want to calculate this, I create a basically integral function 1D, let's say mapped, let's call this mapped func is I don't know why I'm making a mistake here, a typo, Gauss function mapping start end. Okay, and then let's also do the create another one, function mapping, inverse function mapping. Inverse function mapping, we have to use the we have to use the interval. So here t is in -1 or 1. Okay, and so what we are going to do here, we're creating an integral function 1D, which is our mapped function, and then the next thing is to double, these are our weights, and double, these are our points, xi's. All right, and then double sum equals 0, and then let's make this public. Gauss-Legendre, let's say 3 points. So we want to implement the 3-point Gauss-Legendre, and the weights for the 3 points are let's see, the weights for the 3 points are 0 and plus minus square root of 3/5, which is 0.774597. Okay, so the weights are, so the points are 0 and 0.774597 and the negative of this. So these are my points, and then the weights are 8/9 and 5/9. 8/9, 8/9 for 0, and 5/9, 5/9. Okay, and then sum is basically we write an int for int I equals 0, I less than points dot length I plus plus sum plus equals what we are going to do, we are going to get the weights at I times the value of the mapped function at basically the points I. All right, so this is our quadrature rule, and then we return sum. Okay, so let's see what we did here. And so we are creating a mapping of the -1 to 1 to a star to n. Why are we going through this? Because the Gauss quadrature, so basically the closed form equation for the weights and the points are based on the fact that the original Gauss-Legendre are based on the Legendre polynomial if and only if the integral limits are from -1 to 1. So if we are starting with this problem, then we can find the weights and the points with closed form solutions, right? And then we need to solve the problem of integrating from a to b, and for that we use this mapping that a to b f of x d of x is b minus a over 2 times this mapping, this integral of g of x. All right, so what we are given is the function over a and b, so we want to map it to a function which is defined or equivalent to our function over -1 to 1. So we use this g of x. G of x is f of this mapping. Okay, now in this mapping, this x here is between -1 to 1, this x is between a and b. So what we need to do, we need to do the inverse mapping, right? So I want to calculate this first, so I assume that my x is between -1 to 1, If it's the case, then g of x is f of this term. So here in the Gauss-Legendre function mapping, function mapping, what we are going to assume is that we're calculating the value of the function, assuming that t is between actually this, I think this should be reversed, right? -1 to 1, and then this should return the map. Yes, because the interval mapping maps from -1 to 1 to start to end, and then the function is defined over, oh yes, and the inverse mapping, we have to have inverse interval mapping. Okay, so our mapped function is here is t is in -1 to 1. So Gauss-Legendre function mapping, which is the function calculated at this mapped interval, such that this variable is between -1 to 1. Okay, and then we sum the we get the value of the map function at the points, quadrature points, which is defined for a 3-point quadrature rule. So we are doing a 3-point quadrature rule, or Gauss quadrature rule, Gauss-Legendre quadrature rule. The weights points, they have closed form solution as long as our function is defined between -1 or 1, right? So this summation, weights times the value of the map function at these points, it gives us the integral of this mapped function over -1 to 1. All right, and then if we because of this, the fact that we map the interval, it's equivalent to mapping the calculating the integral of the function over over the entire interval start to end. Now the problem is that if the interval is long, is a large interval, the 3-point rule is not going to give you an accurate result, right? So let's go and test it first. In test 4, we had different types of methods, and let's say we want to do t cubed, for example, and Simpson recursive. So I'm going to remove these okay, I'm going to add the Gauss, and in the Gauss I'm going to call the Gauss-Legendre polynomial 3-point. So Gauss 3-point approximation, '32. So we are off by a factor of 2. Oh, that's because, okay, sorry. That's because this sum gives the integral. Okay, so when we did the mapping, we mapped it, but this sum is the integral over basically -1 to 1. And if you recall, here we had this factor b minus a over 2, right? So we have to scale the calculated integral by this factor. So I have to return this sum times basically end minus start over 2.0. Yeah, and the thing here is that we didn't do much. It's extremely simple, only 3 points, and we're getting almost exact result, and it should be, because the 3-point is supposed to be accurate up to polynomials of degree 5, right? to n minus 1. So T3, T4, T5, these all should, the Gauss quadrature should give me exact result. 682. Okay? Simpson returns 682.666, and then maybe let's also try the exact here. If it's T5, I should have n to the 6th power minus star to the 6th power divided by 5, 6. So the exact is 682.666,666, which is basically Simpson. Now the Gauss, as you can, in the Gauss quadrature, as you can see, it gives us 6672. And the question is, why is that is not giving us exact? Because we used the exact results for weight, but we didn't use the exact results for the points, right? We use only 6 digits, 6 decimal approximation. So the exact points or the exact values are square root of 3 over 5. So let's use those. Instead of having these, I use math dot 3 over 5 and the negative of this. Okay, now I'm using the exact values for the quadrature points, and let's try it again. Yes, now it gives us the exact result, 682.66666. Okay, so this is a 5-point or 3-point quadrature, so we can increase it to, for example, 5-point. Instead of 3-point, we go 5 points, and 3.5 point. Everything is the same, the mapping is the same, and then the summation is the same, and then when we integrate over minus 1 to 1, we scale it back. The only thing that changes is the weights and the points. That's the only thing that changes. Okay, and for the 5th degree, we have 0, 1 over 3 square root of 5 minus 2 square root of 10 over 7, and these are the weights. So it's a little bit hard to write, but you get the picture. So one of the points is 0, the other point is 1 over 3 square root of 5. So 1 over 3 times math dot square root of 5 minus math dot square root of 10 over 7. Okay, 5 minus 2 times math square root of 10 over 7. And that's one of the weights. The other weight is the negative of this one. Okay, and there are 2 more weights that we can write them down here, but there are 2 more points. And then let's look at the weights. For 0, the weight is 128, 225. So 128 divided by 225. For the next points, 1 over 3, 5 minus 2 square root of 10 over 7, 3, 2, 2. Okay, let's add the other points. 1 over 3 square root of 5 plus 2 square root of 10 over 7. Square root of 5 minus 2, 10 over 7. The other 2 points are 1 over 3 square root of 5 plus 2 times square root of 10 over 7. And the next point is basically the negative of this one. Okay, let me just go full screen. Alright, so we have 5 points and we need to have 5 weights, and the weight for the other two is 322 13 over, okay, so 322 plus 13 times square root of something over something, right? How much was this? 13 square root of 70 over 900. 70 over 900, and the weights are the same, right? 322 13 square root of 70 over 900 for these two, and for the next ones we have 322 minus 13 square root of 70 over 900. So 322 13 square root of 70 over 900. We just use a minus sign. 322 minus 13, and the next weight is also the same. Okay, and this is basically a similar thing. So let's go here to our test, and let's do Gauss 2, Gauss-Legendre 5 point, and then Gauss 5 point, Gauss 2. This also should give us exact results, but it doesn't. So the 5 point fails, and the question is, why is it we're getting error here? And let's check the weights. 322 minus, and the roots are 0, 1 over 3 square root of 5 minus 2 square root of 10 over 7. 322 plus 13 square root of 70 over 900. We take the weight and then we use the map function over 900 here, plus plus minus minus 1 over 3 5 minus, oh sorry, so the last weight is minus, okay, yeah, so the points come in opposite signs. So 1 over 3 square root of 5 minus 2 times square root of 10 over 7. The next one is negative of that. The next one has a square root of 5 plus, and the last one is minus 1 over 3 square root of 5 plus. Okay, so let's go to our test. Yes, now we get the 5 point, the exact result. And keep in mind that with 5 point, and again this doesn't have any complications or any burden, because we're calculating the original function at 5 points. Remember, we're only calculating at 5 points, and so only 5 evaluations, nothing else. The points are, the weights are given, the points are given. The only thing that we need, 5 evaluation on the function and do the summation. That's it. So that's the power of quadrature, because the weights and the points are predefined. And then we see that up to the polynomials of order, so with 5 points we have to be able to get ninth order polynomials. We should be able to exact result, and that's a very powerful thing. And then the main problem here is that with quadrature, if the interval gets very large, and the error of the quadrature scales up linearly, that's because of the factor b minus a over 2. So when we are integrating over the minus 1 to 1 of this map function, the error is constant, because that's the definition, that's how the Gauss quadrature works. The error is constant. But then the error of this a to b integral is the error of minus 1 to 1 integral times b minus a over 2. So the error scales up linearly with the length of the interval. That's the problem with Gauss quadrature. The solution is to divide the original interval into sub-intervals, but we don't need to do, for example, 100 sub-intervals. We can do like 10 or 20, or based on stop criteria or the error tolerance that we want. So here I'm putting 40, and let's see. And the thing is that here, because the function is polynomial, we should always get the exact result. Let's change it to math.sine of x or sine of t, and let's keep the 4. So we're integrating from 0 to 4. The exact, okay, so the exact result is never mind. So Simpson is 1.85777, and the 3-point quadratures, you see it starts to lose accuracy. It's 1.888, which we know that the exact result is 1.8577. So we have quite some error here. The 5-point quadrature turns out to be very close to the exact result, 1.85778. Okay, so if we want to increase the accuracy, we need to increase the number of points of the quadrature. But after a while, it becomes, it adds more overhead in terms of the calculation. So there is a trade-off between how many points we use for the quadrature, Gauss quadrature, and how many sub-intervals we divide the original interval, okay, into. So if I put 40 here, for example, the recursions, let's also comment out the recursions. Again, I don't recommend recursive approach for integration because there is really no point to that. And as you can see, all of this approximation, especially the trapezoid, Simpson, and the center approximation, center rectangle, they give a pretty decent result, but the Gauss 3-point or 5-point, there is just pretty much garbage. And that's why if the interval is very large, it just loses its accuracy, 3-point or 5-point. Okay, so in the next lectures we look into ways of increasing the number of points, because we cannot just go to a table and try to look them up. We have to be able to calculate them. And then also the other approach is to divide the original interval into several sub-intervals and use a low-point Gauss quadrature for each sub-interval. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on Gauss quadrature method or Gauss quadrature rule for numerical integration, or numerically approximating a definite integral of f of x from a to b. And we said that we need to find some points which are called quadrature points xi to evaluate the function, and then we need to find some weights which are wi, or quadrature weights. All right, and we said that we start by defining the problem of integrating over minus 1 to 1, and the reason is that when we do over minus 1 to 1 and applying the condition is that this approximation must give us exact result for polynomials from degree 0 to degree 2n minus 1. When we do over minus 1 to 1, we are actually able to find the exact solution for the quadrature points and the quadrature weights. And the quadrature points are the roots of the Legendre polynomial of degree n. So if I have n points and we have n roots for the polynomial of degree n, and the weights are related to the quadrature points and the derivative of the Legendre polynomial by this equation. But we have to be careful because this equation is only valid when the Legendre polynomial is normalized, such that its value at 1 is equal to 1. Okay, I mean, for roots, the normalization doesn't matter because the roots don't really care about the actual coefficients, just the ratio of the coefficients. And this table from Wikipedia, we looked at the third 3-point quadrature rule and the 5-point quadrature rule in the previous lectures, and now we want to implement a general case where we specify the number of points we want to use, and then we find the weights and the quadrature points, and then calculate the integration. Now, in order to do that, we have to be able to find the Legendre polynomials and then find its roots and then the weights. All right, and so the first thing we need to do is see how we can find how to implement the Legendre polynomials. So Legendre polynomials are polynomials, right? And in the previous lectures, we already looked at how to implement polynomials in Java. And these are an orthogonal set of polynomials and are only defined over -1 to 1 interval, okay? And over this -1 to 1 interval, they have this orthogonal property, okay? -1 to 1 pn, degree m, degree n. If n is not equal to m, this has to always be 0. And I put 3 different definitions of the Legendre polynomials here. One is through the generating function. So Legendre polynomials are the coefficients of a series with t to the n, such that this series becomes equal to 1 over a square root of 1 minus 2xt plus t squared. And if you're familiar with the physics, and you know that this type of function, square root of 1 over square root of 1 minus 2xt plus t squared, is a Newtonian potential or Coulomb potential in electrostatic or Newtonian gravity. This type of thing happens all the time, and then we can expand it using Legendre polynomials. Now, I mean, obviously this is not the best definition in terms of actually being able to calculate the Pn of x. So the other one is Bonnet's recursion formula. So if we start from P0, which is 1, and P1, which is just x, all right? And then the Pn plus 1 is times n plus 1 is 2n plus 1 x Pn minus n Pn minus 1 of x. So this is one definition. The other one is using Rodriguez formula, which is a more direct approach, right? It's not based on recursion. It's just x squared minus 1 to the power of n, okay? Take the nth derivative divided by 2 to the nth times n factorial. So we have to calculate the factorial, we have to calculate 2 to the n, and take the nth derivative of x squared minus 1 to the power of n, all right? So both of these recursions and the direct approach are easy to implement. So let's head to Eclipse, and we had in the previous lecture we had this project demo polynomials, and we implemented the polynomial class in Java based on the definitions that each polynomial has a degree integer, which is the degree, and an array of coefficients, which has the length of degree plus 1, because we have to go from index 0 to index n, right? X to the 0th power to n to the nth power, so n plus 1 coefficients. And the most important thing was for us to implement the operator overloading for addition, subtraction, and multiplication and negation. And we also had some functions or methods such as toString, and then evaluate, and then which we implemented the most efficient way of evaluating a polynomial, which is Horner's method, and then composition of function, and then the roots. Roots are important here because for Legendre polynomials we want to find the roots. And then so one thing that we need to implement here, the first thing we need to implement is differentiation, public polynomial diff. All right, if we want to find the degree, so int degree diff is degree minus 1 when we differentiate a polynomial. And then when we differentiate, we have to create the coefs. So coefs diff new double, and here because we already know the degree here, plus 1, and then for int I equals 0, I less than coefs diff dot length I plus plus. Each coefficients for the derivative of a polynomial is its corresponding coefficients at index I. Okay, I plus 1. Remember, the 0th order coefficient, a constant term, has a derivative of 0, right? So we don't put it there. And the first term, the first order term, a1 times x becomes a1. a2 times x squared becomes 2a1 times x. So each one is multiplied by its corresponding degree, which is I. All right? Or I plus 1. So the ith term in the diff coefficient corresponds to I plus 1 term in the original derivative, because the first term is 0, right? The 0th term or the constant term of the diff is the first term. All right? And all right, and then we return a basically polynomial for the double coefficients, coef diff. All right. And if we want to diff it with m times diff, this is just the mth derivative or nth derivative. Mth derivative. We just define a polynomial. Let's call this polynomial polydiff equals this. And then for int I equals 0, I less than m, I plus plus, we say that, okay, polydiff equals polydiff dot diff, and then return polydiff. So we make a copy of the original polynomial, and then we differentiate it, assign it to this previous one, so this just goes around like a loop. Okay, and then we return it. So let's go and test this. Okay, I'm going to create a new class here, test diff polynomial. All right, so here I'm going to create a public static void test1, and I'm going to invoke test1 here in the main method, and then here I'm going to create a polynomial p1 or poly1, whatever you want to call it, new polynomial, and I'm going to say that, okay, 1 x 2x squared minus 3x cubed plus 4x to the 4th power. So I'm going to do a sysout on poly1. Let's see the result. 4x4 minus 3x3 plus 2x2 plus x plus 1. All right, I could in fact have one of these equal to 0, doesn't matter. 1x 2x cubed 2x squared 0x cubed plus 4x4. All right, and then let's test derivative. So polynomial poly1 diff is poly1 dot diff, and then sysout poly1 diff. So the 1 constant term in poly1 becomes 0, so we don't see it, and then 1x becomes 1, 2x squared becomes 4x, 3x 0x cubed becomes 0x squared, and then 4x4 becomes 16x cubed. And if we return this, let's say again I don't know, minus 1x cubed, 1 becomes 0, 1x becomes 1, 2x squared becomes 4x, 3 minus x cubed becomes minus 3x squared, 4x4 becomes 16x cubed. All right, and sys out poly1 diff twice. So diff twice, basically this is the poly, this is diff 1. So maybe let's just poly equals, and then diff, poly diff, and then twice diff diff. So so the poly is basically, okay, let me just hide this again. I'll comment this and run it. So what we see here is that again the differentiation works fine. Let's uncomment this. We are differentiating twice, so 1 becomes 0, 1x becomes 1, 2x squared becomes 4x, 3 minus x cubed becomes minus 3x squared, and 4x4 becomes 16x cubed. And then the second twice differentiating is basically differentiating the diff. Okay, so 1 becomes 0, 4x becomes 4, minus 3x squared becomes minus 6x, 16x cubed becomes 48x squared. So differentiation works. All right, now we're going to create in the polynomial, we're going to create a package called special, and in the special we're going to create a Legendre polynomial. In the Legendre polynomial, I'm going to use a static method, use static methods because there is no need to instantiate it. So a private constructor. All right, so no instantiation and just a static method. So public static, let's start with the recursion, right? So in the recursion, we have this Bonnet's recursion, right? So let's go with from Bonnet and int degree. So we have an int degree, public static, we're going to return a polynomial. Again, I typically don't recommend recursion because it has a cost, overhead cost of going into the method stack and then coming back up. So so from Bonnet, or maybe just let's call it Bonnet. And then, or okay, let's keep the from. So from Bonnet, and we have the one thing that we have is the stop criteria and then the return. All right, so the stop condition is that if degree equals 0, we return 1. So remember, for Bonnet we need to have two and these are two initial conditions. If degree equals 1, we return and in order to be able to do operator overloading, I'm going to, from the polynomial class, if you recall in the polynomial class we had a static field which was x, our base polynomial, which is 1 times x. So I'm going to import it as a static member, polynomial dot x. So 1 plus 0 times x, this automatically converts the thing into a polynomial. If degree is 1, we are going to return x, right? These are our stop conditions. If I go back, so p0 is 1, p1 is x. And then obviously we have to check that we can check that or check that. So Legendre polynomials are basically defined between -1 to 1, but here we don't check that condition. We could check that condition at some point, but we don't have to. We can just and what do we do with this recursion? 2n plus 1 times x pn, so 2n plus 1, so return maybe let's just also define n degree 2n plus 1, okay, times x times pn. So if I'm evaluating pn, this should be pn minus 1. All right, so the problem here is that if I put we have to actually, we're looking for pn, so n plus 1. So in my code, n plus 1 should be degree, so n should be degree minus 1. All right, let's keep that in mind, and then I can use exactly this formula: 2n plus 1 x pn minus n pn minus 1. 2n plus 1 x pn. So again, recursion means call the same method on n, and then minus n pn minus 1. N times call the same method n minus 1, and then once we find this thing, we divide it by n plus 1. N plus 1. All right, that's how recursion works. And then I can go back to test div and create another test, test2, and then test2. I'm going to invoke test2, and here I'm going to create a polynomial, and so what we could, two things we could do. So this we could create this as a extended polynomial class, but we decided to go with this kind of like helper class or with static methods. But in fact, we could actually extend the polynomial class. But the problem was that then we had to do one of these we have to invoke one of these two constructors as the super constructor. So let's stay with this. All right, so here in test2, I'm going to say that polynomial Legendre equals Legendre polynomial from Bonnet degree 0. Maybe let's just do the sysout on it. So Legendre 0, 1, 2. So we already know that 1 and 2, 0 and 1 should be 1 and x, and the second one is 1.5 x squared plus 0x minus 5. 3, 4, 5, 6. 3, 4, 5, 6. All right. And what I'm going to do here, let's copy these and then bring it back to our PowerPoint. So let's go to here. I have plotted some of the functions, some of the polynomials. P0 is this green, which is 1. P1 is this one, a linear. P2 is this one, a quadratic. P3 is this blue one, cubic. P4 is this pink one, and P5 is this red one. And let's compare the results. P0 is 1, right? P1 is x, this coefficient is 0. P2 is 3 over 2, 1.5 x squared minus 0.5, yes. P3 is 2.5 x cubed, this coefficient is 0, minus 1.5 x, right? P4 is 35 over 8, which is 4.375. x4 minus 30 over 8, which is 15 over 4, which is 3.75. X squared, 3 over 8 is 375, right? So it's correct. And we can go on, and all these are correct. So our code is working fine. So that's one way of calculating the Legendre. The other one is from Rodriguez direct equation. So public static polynomial from Rodriguez. How do we write it? From Rodriguez. Again, int degree. All right. Here, let's just so what we need to do first, we need to calculate x squared minus 1 to the power of n. This is our polynomial, and in order to do that, we have to be able to create a polynomial x squared minus 1 and raise it to the power of n. Okay. So let's and then so step 1, create this. Step 2 is to dn dxn, so nth derivative of x squared minus 1 to the n, right? Nth derivative of x squared minus 1 to the nth power, and then 2n n factorial. Step 3 is 2 to the n times n factorial. So we have to be able to also calculate factorial. Alright, so let's go to our polynomial class, and here we implemented diff, but we need to also implement power, public polynomial pov, and then int m. So we want to be able to take our polynomial p of x and raise it to the power of n. So we have to be able to basically multiply it m times. So again, you already know the drill. Polymult equals this. We start with a copy for int I equals 0, I less than m, I plus plus polymult equals polymult times polymult, right? We multiplied n times. So the first step, it gives us p squared, and then we substitute it there. Okay, we have to actually multiply it by this. So the first step is this polynomial, and then we multiply it by itself, it gives us this squared, and then multiplied by this again, it gives us this cube, and etc. And then return polymult or polypov or whatever we can call it. And let's go back here and try to test it. Public static void test3, and we are going to invoke test3. And here in test3, what I'm going to do is basically create a polynomial. Let's say a simple polynomial, x squared minus 1 and then x minus 1 0x x squared. So let's do a sysout on poly 1. Maybe let's just first create something simpler like x, and then boom 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 pov like 2, pov like 3, and pov 4. Okay, so we have x, we have x cubed, so what happens here is that I believe we shouldn't start from this, or if we start from this we should reduce the order by 1, right? Because if m is 1, power of 1, if I keep this like this would, if m is 1, it means it's power of 1, so it should return this, but here I'm getting this squared, so I have to yeah, so this makes sense. If m is 1, we never go through this loop. If m is 2, we only do this loop for once. Okay, now this should work. Yes, so x squared, x cubed, and x to the 4th. That's correct. So see, the problem here is that it's actually increasing the order, right? And that's not good. So we can right now we don't care that much about this, but what we can do here is we write a method called let's public double a public polynomial reduce coefs. So what this does is starts to remove the zeros from the trailing coefficients, remove zeros from higher order terms. So we create a double reduced coefs, and then basically what we can do here is we start with an index equals 0, or maybe degree. So if we have the coefficient array goes from 0 to degree, so we start with degree, and then for int I equals and we can say while math dot abs coefs index is greater than or less than 1 in negative 9, that's our, or minus 1 in negative 10, that's our threshold for 0. Then we're going to index minus minus. So what happens here, we start with the last term and check whether or not this coefficient is pretty much 0. And again, because we're using double numbers, we cannot do the exact equality. That's not recommended. If it's 0, I increase the index and I go all the way until I hit the first non-zero term, okay? And once I do that, what I do is I have the index, and then now that I have that, I create an array of reduced coefs, which is new. Now I know the degree, right? From 8, for example, here I go to 4. A new double is just coefs or degree minus index. Actually, it's just index, right? Eight, 7, 6, 5, 4. So the first index is the degree of the reduced polynomial, and then return new polynomial with these new reduced coefs. Okay? And now here, what I'm going to do here, when we do the diff, for example, I return the polydiff time dot reduce coefs. And when I do diff, I also return. All right, before that, let's go and try the reduce. So public static void test4, and here I define this polynomial, and then let's do a sysout on poly1. We're going to invoke test4. X squared plus x plus 0, okay? And now let's do a sysout on the poly1 dot reduce coefs. It just says 0. And that's a bit odd. That's because we didn't, okay, so for int we didn't assign the coefficient, there's just 0. For int I equals 0, I less than index I plus plus, I actually equal to index, right? And so index is the new degree, so this should be degree plus 1. And reduce coefs dot length or index plus 1, I plus plus, reduce coefs I is equals coefs I. All right, now we assign them. Let's do the semicolon, and let's just refactor, rename it to just reduce. Okay, so now we have we don't have the x squared anymore, we only have x, so it works. Let's see, 0 minus 1, for example, so we have minus x squared. It shouldn't do anything wrong. Yeah, it's the same thing. X squared, 0x cubed, 2x to the 4th, right? But let's say this was actually 0, so I don't have an actually 3 x to the 4 or x to the 3 term. So This should already reduce the coefficients for me. That's correct. So I don't get these two terms anymore. So the reduce is working. Now in the polynomial, in the diff, when I do the diff, I return the reduced version. Actually, it's a good idea to return the reduced version in all the methods. And so even in the pub, I return the reduce. Okay. So now if I go back here and then invoke invoke test 3, which is power to the increasing to the powers. Now the original poly is 0x squared plus x plus 0, so it's only x, right? This p of x equals x. And then power 2 is x squared, 0x0. Power 3 is x cubed, 0x squared, 0x0. And power 4 is x4 and x cubed, 0x cubed, 0x2, 0x0. So that works, and all of these are reduced nicely. All right, and let's go back here. So we want to calculate so we create a polynomial. Let's call this the base is x times x minus 1 to the power of degree. All right, and then let's define polynomial diff base is base diff degree times. Okay, and then finally we need to calculate 2 to the nth times factorial. In order to do that, I'm going to use the function factorial that I wrote in my math utils class. And remember that factorial in general should return an integer or long, but here I'm returning a double. The reason is that then it allows me to hold more digits, more precision. All right, so I'm going to give a dependency, which I think it already has a dependency on the math util. Yes, mathlib. So double coef is math.pow to the degree times math utils dot factorial. We can take a double value and return a double value and its degree. All right, and eventually return the result. So eventually we're going to return coef times diff base. All right, so let's go here and let's copy test 2 and test 5. We're going to invoke test 5, and here I'm going to do a sysout on bonnet. So the first one is bonnet, and maybe let's also when we do this, let's also try to reduce it, dot reduce, and we could also do that here. Actually, it doesn't really, okay, it doesn't matter. And then do exact same thing from Rodriguez. From Rodriguez let's run. All right, let's see. 1 from Rodriguez, we get x squared minus 1. So Rodriguez is seemingly is not working. The question is why, and the answer is because we are multiplying by coef instead of dividing by coef. So let's multiply it by 1 over coef, or just divide it by coef. So the coefficients are so the Rodriguez why are we getting the 0th term? That's because if degree is 0, okay, so we have to go here in the powering. If m equals 0, we're going to return 1 plus 0, basically 0 times x, constant poly, right? P of x equals 1. We're going to just return 1. We could actually, okay, yeah, for m1, okay, so the problem, I guess, with powering is 0. And the same thing with diff. So what diff is fine, because if m is 0, we never go through this loop, so we end up with the same polynomial, right? So this should work now. Yeah, so we end up with 1, and in the bonnet we could also reduce the polynomial. Let's call this the result, and then we just say, okay, return result after reducing the coefficients. All right, 0x plus 1, 1, x, 1.5x squared, 0x minus 5, and all the way to the 6th degree, which are exactly identical. All right, so this was the introduction on how to calculate the Legendre's polynomial. Now that we have the Legendre polynomial, it's very easy to implement the general case of Gauss quadrature, which will be the subject of the next tutorial. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration using Gauss-Legendre quadrature method. And we said that when we're trying to solve the problem of integration over minus 1 to 1, the quadrature points xi and the weights wi's have closed form solutions. Xi's are the roots of the Legendre polynomial of degree n, and all the roots of a Legendre polynomial are distinct roots. They are all real roots, and they have odd parity. So if, for example, we look at the 3rd degree polynomial, it should have a 0 root, and then the other 2 roots have opposite parity, plus and minus. They equal and opposite, okay? So all the roots are real, distinct, and all of them are in minus 1 to plus 1. So maybe I'll write it here. All roots are in minus 1 to 1. And we also said that the Legendre polynomial, based on the definitions that we discussed, like the Bonnet or Rodriguez, they might result in So based on the definition what we choose, we might not get this normalization. So the weights have this equation. Only the Legendre polynomials are normalized at 1 at the endpoint, right? To be 1. So, and now what we are going to do is we also calculated, we implemented these two methods, the Bonnet's recursion formula and Rodriguez formula, by extending our polynomial class to be able to take the nth derivative and also taking a polynomial to some power, raising it to some power. And now what we are going to do is we're going to implement the general Gauss-Legendre polynomial with n points. So we should be able to find the roots of the Legendre polynomial and also the weights. So let's head to Eclipse. So in our demo polynomial package, we already have this Legendre polynomial that has two methods from Bonnet and from Rodriguez. And in the integral 1D, what we are going to do, we're going to create another method, public static public double Gauss-Legendre, and then we're going to have double start, double end, and int num points, number of points, or num quadrature points. And then, so what I'm going to do, I'm going to create a variable n, num quadrature points. We actually don't need to, just call it quadrature points. And then here, what I'm going to do, remember what we're trying to do here. We're trying to integrate over a start to n. So we have to do the mapping first, create an integral function, which is called the map function, and maps the original integral function to -1 to 1. And then the rest is basically the same here, right? And the only thing that is different, maybe let me just write it. So double weights, new double, we have n quadrature points, so n weights, and double quad points. Let's call this points, just points, and new double n. All right. And okay, I'm going to also put this here and create weights and points, and then integrate over -1 to 1, and then scale to interval start end. And the way we scale it with n minus start over 2. So so we're basically having the same thing here. We create the sum, we do a for loop to integrate over -1 to 1, and then scale it back to a start end by doing n minus start over 2, right? Half of the length. Now what we need, we need to use our Legendre polynomial to create the weights and points. So what I'm going to do, I'm going to give this a dependency on the polynomial project. Demo polynomial. Let's also remove the dependency on the mathlib, and here I was using this timer class, so let's also comment this out. We also have the export, so let's also remove the export, Command Shift O. Okay, now we need to create the weight. So we said that the Legendre polynomial, so we're going to create the Legendre polynomial. polynomial Legendre n, or Legendre is Legendre polynomial. Let's use the bonnet, which was recursive, and then we are going to use n, which is the quadrature point. All right, and then here we're going to get the roots, and so and the weights. So for int I equals 0, I less than weights dot length, or it's just n, right? I plus plus weights dot weights I equals what? So what we need to make sure that here is to normalize it. So Legendre equals Legendre divided by Legendre evaluate at 1. We gotta make sure that we normalize it to its value at 1, although most likely it is 1. All right, so weight is 2 divided by 1 minus points I squared, okay. So let's go back to the definition. 1 minus xi squared times p prime xi squared times so maybe let's double c1, 1 minus point I squared and then double c2, and then eventually weight is equal to weight I is equal to 2 over c1 times c2, and c2 is basically Legendre. We're going to take the derivative and then evaluate it at points I, right, at xi. I could just let's also do a refactoring to make it easier. All right, so this brings it closer to the actual equation, weights and x, and okay, maybe let's just keep it like that. Points and weights. In the points, 1 minus point I, so 1 minus xi squared, 1 minus xi squared, and here I'm calculating p prime order n, okay, p prime at xi, and I have to square it. So let's call this double c3, c2 times c2, and here we put c3 as the weight. All right, so that's it. But now what we need to do, we need to get the roots first. So normalize it, get the roots, get the weights. So how do we do that? We call the Legendre dot roots, right? Now this is absolutely not the most efficient way of getting the points. There are other algorithms that are better in terms of approximating the quadrature points and weights, but here I'm just calling it just the roots and finding the roots. And this roots method, if you recall, this returns a complex. So and let's go back to this method. It has the complex type from the Flanagan package, which is in our mathlib. In one of the reference libraries, we have this Flanagan here. So I'm just going to use this. access modifier, so complex C roots or complex roots. All right, but then I need to have a dependency on it, so I'm going to add a dependency on the mathlib, and now it finds it because in the mathlib I have added if I go to the mathlib build path in the export, I have enabled the mathlib project to export Flanagan package, right? So when I add a dependency on the mathlib, it already adds a dependency on the Flanagan package as well. All right, so we are getting the roots, but these are complex, and we already know that all the roots are real. All the roots are real. All right, so what we are going to do, actually we can test this. So let's go to test polynomial, actually test diff public static void test 6, for example, and then Legendre polynomial, let's say we get the 6th degree, and we get the root. All right, and then for complex, or maybe for int I equals 0, I less than c roots dot length I plus plus, we just do the sys out on the c roots, and they should all be real. Test 6, let's invoke test 6, and yeah, so all of them are real, so all roots are real, all roots are real with opposite parity. So if x0 is the root, then minus x0 should be the root, and also the other thing is that all roots are in -1 to 1 interval. They should all be there, and that's the case. Minus 0.932, minus 666, and minus 0.2386, plus 0.2386, 0.06612, 0.9324, and for the odd order or odd degree, one root should always be 0. Okay, so what we are going to do, okay, let's close this, let's close the polynomial here. What I'm going to do, I'm going to say for int, so all of these roots are real. C roots dot length I plus plus points I is equal to C roots I dot real. Get real, which returns a double value. All right, we get the points, we get the weights, and then we get the results. Now let's just print the weights and points to make sure that our algorithm is correct. So we do a sys out on, let's say, arrays to a string of a double, let's go to the arrays class. It has two string methods, int char byte object. So we're going to a string points, and let's call this points equals plus arrays, and also weights. All right, now let's create a new test class, test Gauss-Legendre or test Quadrature. with a main method. I'm going to create a test, public static void test1, and here I'm going to invoke test1. Alright, and now in the test1, what I'm going to do, I'm going to create an integral, or maybe create an integral function 1D. Func t goes to t times t, for example, and then I'm going to create an integral 1D integral finder, new integral 1D. I'm going to pass in our integral function, and then double integral or double result is integral finder dot Gauss-Legendre 5.3 just Gauss-Legendre 0 to 4, let's say 3 points, which we already know the coefficient. Sys out on the result. So the points, the result is 21.333, and this should be exact because a 3-point Gauss-Legendre quadrature should be exact for polynomials up to so let's just also calculate the exact. So it should be exact for up to twice the degree minus 1, 2 times 3 minus 1, 5th degree polynomials. So the exact is math dot power of basically 4 to the 3. That's just 4 times 4 times 4 over 3. Yes, so the exact is, and then we get the points and weights, and let's compare them with what already we had in the table before. Okay, so points are 0, and its corresponding weight is 0.8888, which is 8 over 9. All right, and then we have plus and minus 0.774597. The most accurate one is 0.77459666 is. All right, and then its corresponding weight is 0.55555. So here 0.55555, so which is 5 over 9. So that's the corresponding weight, which is accurate. Now let's try the 3rd degree. Let's try the 5th degree, the 5 or 4. And these are the points and weights. Okay, let's compare it. For we don't have any 0, we have plus minus 0.33998. Here we have plus minus 0.3399981. all right, and plus minus 0.861136. okay, and the corresponding weights are 0.652145, all right, and then 0.347855. okay, so our Gauss quadrature seems to work just fine. Now if you recall, when we were testing the integration, what we said that is the problem is that if the interval is long, very large, let's say from 0 to 40, the error of the Gauss quadrature scales up with because of this scaling factor b minus a over 2 and the mapping that happens from ab to minus 1 to 1. The error scales up. And then there are several ways to compensate for that. One is basically as we increase the number of quadrature points, the number of terms, the error goes down. So we can in fact increase the number of quadrature points. So Gauss 3, I'm going to call the Gauss here, Gauss-Legendre with the number of here, let's say 40. Points. So 3 points, 5 points, 40 points. And I'm integrating t times sine of t from 0 to 40. So let's see what happens. So this is our test 4. So as you can see, the 40-point quadrature is still working. So it's takes some time to find the roots. So that's not the best way to implement it. So let's implement, let's say 5. Okay, let's also comment this out. So we don't want to print the... So the 5 points are basically the same, which is not good. Let's go 10 points. Not good. 15 points. It's getting better. 15 point is getting pretty close. 27.5028. Simpson is 4228. Let's go 20 points. 27.389. We're getting closer. 25. No, it's getting worse. 35. Now it's taking a lot of time. So definitely it's not a good idea to try to just increase the number of points, right? So what is recommended here to stick with a smaller number of points, let's say 5 points, all right? And then instead of increasing the points, divide the interval into smaller sub-intervals. So I have this Gauss-Legendre, and that tells me the quadrature point. And then what I can do, I can define another method, public double Gauss-Legendre, double start, double end. All right. And what I'm going to do here, I'm going to do something similar to what we did for example, for forward rectangle, just a simple summation. So what we're going to do, break the interval into a smaller sub-intervals, and then use 5 or 10 point Gauss quadrature. Now if the interval is small enough, 5 point or 10 point are pretty good, and they're pretty fast, right? So we even have the basically exact roots for, we don't even need to calculate the polynomial and find its root, we already know them, right? So what we can do here is so I'm going to define a sum which is 0 originally, int num intervals is let's say we're going to break it into 100. All right, and then we're going to have the x endpoints, which is I'm going to use from math utils using the linear space, or we can just define our delta x, double delta, which is end minus start divided by num intervals. Okay, and then in each sub interval, so I'm going to create double x, which is a new double num intervals plus 1, and then for int I equals 0, I less than x, I plus plus. And actually I don't need that, so I just write the for int I equals 0, I less than num intervals I plus plus. I do the summation and call the Gauss-Legendre 5-point start. My start is basically start of the interval plus I times delta, and the end of the interval, sub interval, is start plus I plus 1 times delta. Okay, and then I return the sum. So what I'm doing the same routine, dividing into sub intervals, but in each sub interval I'm calling the 5-point Gauss quad instead of Simpson or Trapezoid Gauss quad method. All right, let's test this one. So we have a 40, okay, and guess 4 Gauss 5-point sub intervals. Gauss-Legendre. So remember, I'm breaking into 100 sub intervals, and it pretty much is pretty fast, because 5-point Gauss quadrature is pretty fast. All right, and now we have sub intervals, so in each sub interval we calculate it and then we sum it up, and it's roughly similar to the Simpson, 27.4228563. all right, so they're pretty close. And let's just look at the sign. This is a periodic function, so let's see what happens. Forward approximation is not good, backward not good, center trapezoid 1.644, Simpson 1.66695, and Gauss 5-point with sub intervals is 1.66693, so it's pretty close to Simpson. All right, now this should be more accurate if we increase the number of points here. So instead of basically if I go here, instead of having a 5-point, if I call the Gauss-Legendre and let's say 10 points, okay, then each time, the problem here is that each time I'm calculating the points and weights again, which is not efficient at all. So that's not a good way to do this. It's better, because the points and the quadrature points and weights are fixed for 10 points, right? No matter what the function is, no matter what the start and end is, right? So this is not an efficient way to do it, but let's just try it. 1.6669379. So this has to be the most accurate one. And if we go back and change it to 5 points again, Gauss-Legendre 5 points. So here the weights and points are fixed, so we're not calculating them. it's still the same, right? So the 5-point Gauss quadrature is accurate enough. Now you can make it in a bit more adaptive in terms of keeping track of the convergence instead of having to set the fixed number of intervals or number of points. So if in my math lib class I have in the integral package, I have this integral 1D class, and it's more of an adaptive integration. So I start with 10 sub-intervals. So I break the original interval into 10, and then I start with 5 points for Gauss quadrature, all right? And then I set a limit for the maximum number of iterations. And then what I do here, in the get integral, I look at the absolute error, and then also make sure that the number of intervals is less than some max number of iterations. So if the convergence is not reached, I increase the number of intervals by 10. Okay? And then all right, and then in each sub interval, I do the Gauss quad with the number of points, which is initially set to 5, right? So I'm doing 5-point Gauss quad with an adapting way of increasing the number of intervals. So if with the original 10 sub intervals we don't get a good convergence, I increase the number of intervals by 10, and then I increase the number of iteration by 1. So in each iteration step I increase the number of sub intervals by 10. All right, and then I compare the current result, the new result, with the old result. All right, and if the difference is basically less than the error bound, then this is basically the relative error, then I call it the convergence. Okay, if not, I continue until either the convergence is reached or I hit the maximum number of iterations. But the Gauss quad is always kept at a fixed number of points, which is initially 5, and you can change it using this setter function. All right. Okay, so the last thing that we're going to discuss on this topic is the other types of quadrature. So we can generalize this quadrature concept, and the reason is that sometimes we have some integrals that the function f of x, even if I'm integrating over -1 to 1, the function might have some discontinuity at one of the two ends. It becomes it has some singularity, right? So if f of x has some singularity over the a and b interval, we cannot directly map it to -1 to -1 to 1, because then one of these two limits or both of them could be the singularity over -1 to 1 interval. Or sometimes one of these limits of the integration a and b are infinite. A could be -infinity, b could be +infinity. And again, for these cases the Gauss quad doesn't really work. So what we need to do, we can define a weighted integration. So the idea is that instead of integrating f of x dx from a to b, we integrate a to b w of x f of x. This is extremely important when we're dealing with the discontinuities of f that go to infinity. Then this weight function can regulate them, and more likely it can suppress those very high irregularities in the function values. Okay? So we're going to calculate this weighted integral using quadrature method instead. So instead of calculating integral of f of x, we calculate wx f of x. And there are ways to choose this weight function based on the type of singularity that the function has. So if the function doesn't have any singularity over a and b, it's well defined. So when we map it to -1 to 1, the function is perfectly defined in -1 to 1, also at the edge points -1 and 1, and therefore the weight functions are 1, and the orthogonal set of polynomials that we use to find the weights and quadrature points are the Legendre polynomials, as we saw previously. But if f of x has singularities at both endpoints, then we can use Jacobi polynomials, or another type is Chebyshev polynomials of the first kind. All right. Even if the function doesn't have any singularities, we can still use the Chebyshev polynomials of the second kind. It's still fine. We can find the weights and the quadrature points. If we are calculating the integral from 0 to infinity, so infinity is automatically a singularity for the function, right, for the integration. In order to suppress this, especially if the function goes to infinity at the infinity, we can suppress those fast growing values by a fast decaying function, which is e to the negative x. And this results in the Legendre polynomials for the orthogonality. And the orthogonality is then defined based on this weight function xk pn of x. All right. Or we can choose, if we are doing minus infinity to plus infinity, we can have a much faster decaying function, which is e to the minus x squared. This is a Gaussian function, and the orthogonal polynomials for determining the weights and quadrature points are Hermite polynomials. All right. So the idea here is that if the function has singularities, which are most likely of type infinity, so if f goes to infinity, that's the main problem with the integration. If f has singularities but it's not infinity, it just happens to f not being defined at some discrete point, it doesn't matter, the integration doesn't matter. But if f goes to infinity, we can use this weighted integration and suppress those high values by choosing a decaying function. All right. So this was the main idea of quadrature methods for numerical integration, and they are the most widely used methods when we deal with numerical integration. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on numerical integration of functions, and I'm going to extend our analysis of one-dimensional integration to two-dimensional and three-dimensional, and in general higher order dimensional integrals, right? So how do we do that? So in 1D integration, we had an interval, a one-dimensional function, and we were integrating over one-dimensional using the definition of Riemann sum. Now for higher dimensionals, for example two-dimensional or three-dimensional functions, we can still define the Riemann sum, but then we need to also have the concept of a domain of integration. So the domain of integration is not simply an interval. It's for example, if we are doing a 2D integration, the domain of the integral is basically part of a 2D plane. Let's call it the xy plane. If x and y are the variables of my 2D function, then the domain could be something like this, a rectangle which has well-defined boundaries. So this is one concept that doesn't exist for one-dimensional integration, because for one-dimensional integration the boundaries are always well-defined. We always integrate from A to B. But in two-dimensional or in general higher dimensional function, higher dimensional domains and integrals, the problem here is that the boundaries might not be all aligned with the coordinate system, with the axis of the coordinate system. So in this case, this 2D rectangle is a very nice integration domain or integral domain, right? Its boundaries are all aligned with the axis of the coordinate system. But for example, this one is another 2D domain, could be a domain of integration, but the problem here is that this domain is not a well-defined domain, because although the two boundaries in the x direction are well-defined from A to B, and one boundary in the y direction is also well defined, this HC, but the other boundary is actually a curve, let's say g of x. So at each position in the x direction, at each point x between a and b, y goes from c to g of x, to this curve, right? So this boundary is not constant, is not well defined. So this boundary is actually changing as we change along the horizontal axis. And that's one of the main complications of higher degree integrations, right? So besides having a 2D or 3D integral function as an interface, we are also going to introduce the concept of domain as an interface object in Java. So we have a 2D integral domain and 3D integral domain, right? And to refresh your memory, unlike the first one-dimensional integration, in 2D and 3D, we could have different coordinate systems. For example, in a two-dimensional integration, one coordinate system could be x, y, another coordinate system could be a rotated version of x, y, or could be a polar coordinate. At each point we have a distance from the origin as one coordinate and the angle from the horizontal axis as the second coordinate, so r and phi. And then the 2D dx times dy, which is the element of the 2D element of the domain of integration, or the surface element, is dx dy, which is equal to r times dr d phi. So the element, the differential element of the domain of integration might not be a constant. It could also change with where we are with the coordinates of the points, because of the coordinate system that we choose. So there is no uniqueness of the coordinate system that we choose to do the integration. And if you're familiar with higher dimensional calculus or vector calculus, you know that we go from the differential elements of one coordinate to another using something called the Jacobian matrix, the Jacobi matrix, and the determinant of that Jacobi matrix is called the Jacobian of your integral domain, right? So if I relate x and y coordinates to r and phi, the relation or the determinant of that Jacobian matrix, Jacobi matrix, or the Jacobian of the coordinate system is r. Similarly, in three-dimensional, we have dx, dy, dz, and we can use spherical coordinates. And instead of having just dr, d theta, d phi, we also have a factor r squared sine of theta. So r is the distance from the origin, theta is the angle from the z-axis, and phi is just similar to the polar angle. It's the projection of the point on the xy plane and the angle of that point from the horizontal axis x, right? All right. So there are more complications when we compare them to 1D integration, right? And as I mentioned, the variables could be connected to each other. So if I'm integrating some 2D function over a 2D domain, the function f of x, y, a 2D function, or a 3D function f of x, y, z. Sometimes I may be able to write f of x and y equal to some function of only x times some function of only y. So it's a separable function. But most of the time it's not. Let's say f of x and y is x plus y. It's not a separable function, right? So the integrand or the integral function connects x and y, or bounds x and y's together. Now sometimes the domain bounds, the bounds of the domain of integration connect x and y, and that's exactly this case, right? So in this rectangular domain, the domains, the x and y, are not related to each other. They're completely independent of each other. But here in this case, we can choose x as the free running variable. We call it the free running variable, which has the fixed bounds a and b. But then y becomes a dependent variable, because at each x, y goes from c to some function g of x. So this g is a function of x, and as we move along the x, then the bounds of the y changes. Now in this case, we have to first integrate over y, because y is the dependent variable. Its bounds, or the result of integration over y, depends on x. All right. And one of the fundamental properties of higher order integration or higher dimensional integration is the separation rule. So if the boundaries or the bounds of the domains are independent in each direction, let's say we have two variables x and y, and the domain of integration over x is a to b, and the domain of integration over y is c to d. So there is no g of x, there is no dependence in the domains of integration. And this type of domains are basically a very nice rectangle domain or a cubic domain in the 3D dimension, rectangle in 2D, okay? And the other thing is that if the function is actually a separable function, so if I can separate f of x and y into some function of only x times some function of only y. So if the bounds of the domains are independent and the function is separable, I can write the 2D integral into the multiplication of two 1D integrals, okay? One is over this function of x only over the bounds of x, and one over the function of y only over the bounds of y. And if you just think about it, this is basic summation, right? We have a double sigma summation at each point x and y, and that's the basic property of summation, that we can factorize it if the variables are independent, okay? So when you think of integration, you can think of a Riemann sum, the limit of a Riemann sum, right, as in the case for the 1D integration. All right, so this is the basic rule. Most of the time we cannot use this, but we should have in mind. So let's head to Eclipse, and in our demo integral project, so far we have an integral 1D and integral function 1D. Now we need to define an interface integral function 2D, okay? And here again, let's annotate it with functional interface, and we have to have an abstract method, double, returns a double, and the method is called value, and it has two parameters, double var1, double var2. Let's call them var1 and var2. The reason that I'm not calling them x or x and y is because of the choice of coordinate system. So we want to stay as general as possible. So var1 could be r, var2 could be theta. So we could be integrating using a polar coordinate system, right? So the coordinate system could be anything in the two-dimensional space, two-dimensional plane. But then the other thing is that we have to go and define something called the domain of integration. So integral domain 2D. All right? So we have an integral function 2D, integral domain 2D. This is not a functional interface, but what is this? Let's go back to our presentation. So what do we want from the domain? So the domain of integration in 2D should give us first of all, we can always choose one of the two variables as the free running variable, the variable that its bounds are constant, are fixed. Let's call it var1. So let's assume that var1 is the free running. So this integral domain interface should give us the limits, or the lower bound and the upper bound of this variable var1, okay? And then it should also give us the bounds of the second variable, but the bounds of the second variable, because in general it could in fact be a dependent variable. Its bounds could actually depend on the first variable, which was the free running variable, okay? So when we define the method get var2 min, get var2 max, these are the bounds of the second variable. We should give a parameter which is var1. So the bounds could be dependent on the first or free running variable, all right? Similarly, for the third domain, 3D domain or higher dimensional domains, we start with var1 as the independent variable, so its bounds are fixed, are constant. var2, the second variable, could only depend on the var1, okay? And the third variable could depend on all the previous variables. So var3, min and max could in fact depend on the var1 and var2, okay? And you can easily extend this extend this to any higher dimensional. If we had 4 variables, the bounds of the 4th variable could depend on all the previous variables, so var1, var2, and var3. All right, so this is a very important concept that I want you to understand it very clearly. The way we define the domain of integration is that one of the variables, or the first variable, could be the free running variable with constant or fixed bounds, and then the second variable, the bounds could actually depend on the first variable, and so on. The third variable depend on the second and the first variable. So here in the integral domain 2D, I'm going to define a variable, a method double get var1 mean, and it's fixed, so it doesn't have any parameter. Double get var2 get var1 max, so we're getting the bounds of the first variable, which is the independent variable or free runner. This is the free runner, its bounds are fixed. And then the dependent variable, and in the dependent variable, the bounds could in fact depend on the first variable. Get var2 mean, so it could depend on the var1, and double get var2 max, double var1. All right, and similarly we can define a 3D domain of integration. So another interface, integral domain 3D, and again we have a free runner or independent variable or free runner, and my convention is that it's the first variable, or var1, double get var1 mean, double get var1 max, and then the first dependent variable, it could depend on the first variable, so double get var2 mean, so it can accept a parameter double var1, so double get var2 max, double var1. All right, now the second dependent variable, so the second dependent variable, the bounds could depend on all of the previous variables, so double get var3 mean, double var1, double var2, double get var3 max, double var1, double var2. all right. So this is how we define the domain, and it's a general domain regardless of the coordinate system that we choose. This is a very important concept. I want you to just forget about only the Cartesian coordinates. We can have any sort of curvilinear coordinate system in 2D, 3D, or higher dimensions. All right, so we have our integral function. Let's also define our integral function for 3D case. Integral function 3D, and again this is a functional interface, and we're going to have only one method, abstract method, double value, and it takes 3 variables, double var1, double var2, and double var3. all right, and now let's see how we're going to actually calculate the integration. So let's start with the 2D integration. We already know how to calculate 1D integration, right? Gauss quadrature was pretty good, and we're going to use that for 1D integration, or Simpson, or any 1D integration method that had a very good error order of magnitude for the error. All right, so it's good if we could break the 2D integral into 2 1D integration. And the way we are going to do it is obviously one of the variables is a free running variable. So in terms of x and y, here we're assuming that the x is the free running variable, so its bounds are fixed. So when I'm integrating over x, I'm basically it's like a 1D integration, right? From a to b of some function of x dx. Eventually that should happen, right? So that's one of the 1D integrals. What is the second one? Is so the second variable can be a dependent variable, which means even if my function depends on x and y, the bounds of the y variable could depend on the x, and when I integrate over y, it returns, the whole of it returns a function of x, right? So we must integrate over the dependent variable first. And if we have 3 variables, so for 2 variables, if y is the dependent, we have to integrate over y first. And it's a 1D integral. So in step 1, we define a 1D integral, okay, from the bounds of integration, which in fact depends on the first variable, x here, of f of x and y dy, right? Now the problem is that f of x and y, in terms of Java terminology, f of x and y is a integral function 2D, the type of this object, right? We're going to have an integral 2D object, pass a integral function 2D, which defines the f of x and y into it. And we should also pass a domain of integration, okay? So, and then this is a 1D integral, and we define it as a integral 1D object. And it accepts an integral function 1D interface, not an integral function 2D interface. So we have to do some sort of conversion from integral function 2D to integral function 1D, all right? So we do the integration over the dependent variable first, with the consideration that the bounds could also depend on the variable x, okay? And then once we calculate this, we now have a function of the first variable with fixed bounds. X and b are fixed because x is considered to be independent variable here. And this is exactly a 1D integration. So this is the way that we can break the 2D integral into 2 1D integration, all right? Similarly, the same for 3D, but let's head to Eclipse and try to implement it. So we're going to have an basically integral 2D object, all right, just like the first dimension. And this is going to get let's say private integral function 2D func and private integral domain 2D domain 2D, all right? And then the constructor integral 2D is going to accept an integral function 2D and an integral domain 2D, okay? So we have to pass the function and domain, a 2D function and 2D domain. This dot func equals func, this dot domain 2D equals domain 2D, all right? Or let's just call it domain, okay, domain 2D, all right? And now again, we could have different methods for doing the integration. I'm just going to have one method, public let's say public double Gauss-Legendre double start. I'm going to use the Gauss-Legendre function from 1D, okay, Gauss-Legendre double end. So if you recall, we had this in the 1D integration, and in the integral 1D, the way we defined the Gauss-Legendre here was that to divide the interval into 100 sub-intervals, a fixed number, and in each sub-interval we are using the 5-point Gauss-Legendre and then doing the summation and the integration, okay? So the same thing here. So what I'm going to do, what do we need to do? Step 1. Step 1, we have to calculate that 1D function, 1D integral of the dependent variable. So eventually I'm going to have an integral 1D, integral like let's call this integral 1 equals new integral 1D, and I'm going to pass a integral 1D function, okay? Let's call this something so I'm going to call it func1, for example, or func1D, and then what I'm going to do, I'm going to return integral 1, let's call this integral 1D dot Gauss-Legendre from start to end. Okay, so we don't have to, we shouldn't specify the start and end here. What we should specify is basically what is the start and end. Remember, the second, this is going to represent our last integral, step 2. This is the last 1D integral of the free runner or free variable or independent variable. All right, so the start should be, we call the domain 2D and get var1 mean, and domain 2D 2D get var1 max. All right, now we need to define this, but this func1D is an interface, right? Function 1D interface, so integral function 1D, right? Let's call this func1D. So what is this? This comes from the integration of this 2D function over the dependent variable. So this should come the result of an integral 1D, okay, of some function 1D, one-dimensional interface, and we're going to so let's say its variable is so this is going to function of var1, right? So var1 goes to this get or Gauss-Legendre. Again, I'm going to do the Gauss-Legendre again. All right, now what are the bounds of this? So this the bounds are the bounds of the, remember we're integrating over var2, right, the dependent variable. That's our assumption. So this function we integrate over our 2D function, and let me also call this a func2D. We're integrating over our 2D function, all right, using an integral 1D object, Gauss-Legendre method. This returns a double value, all right. So the result should be somehow dependent of the var1, because then this functional interface is dependent only on var1, and then we pass it to another integral 1D using the bounds of the var1. So obviously these two bounds should be the bounds of the var2, right? Domain 2D get var2. Now this is where the dependence on var1 comes from. Remember, I told you the bounds of the dependent variable could in fact depend on the independent variable. So the minimum, the lower bound of the var2 could depend on var1, and similarly the maximum also could depend on domain 2D dot get var2 max with couldn't. So the bounds of this integration can depend on the var1. Now what to do with function? This function 2D is a function, integral function 2D object or interface, but we need to pass integral function 1D to this integral 1D. So what we're going to do is that say, okay, var2 goes to func2D value var1 var2. Okay, now it says that the constructor integral 1D integral function 1D is ambiguous, and the reason is that, let's do this. So the reason is that in the integral 1D function we actually had two different interfaces that return a double value, right? So that's the ambiguity. So let's I guess there are different ways to maybe we can just define another integral function 1D, or I can, instead of lambda expression, I might be able to use a basically anonymous class. So new, yeah, we should new integral function 1D, And in the anonymous class, what I'm going to do, I call this variable var2, and I'm going to pass in func2d dot value var1 var2. All right, now there is no ambiguity in what interface I'm using. So here the problem was that both of these interfaces are returning a double value. So when I was using the lambda expression, it didn't know which object to create, right? Because both of them return the same double value. But now I'm defining based on an integral function 1D, and var2 is going to be the variable. We plug the numbers in the var2 first, and then var1 is just there. So this interface, integral function 1D, the variable is var1, and var1 appears in two places. One is inside the function 2D, and two inside the bounds of the 1D integration. All right, so this is how we define it. Now we can do this for any type of forward, backward, rectangle, Simpson, or anything. So but first let's go and try to test this. So let's test integral 2D with the main method. And here I'm going to have a method called test1, and let's just create it. And in test1 I'm going to create let's say our example is going to be area of a rectangle, let's say 0 to 4 and maybe -1 to 1. So the area should be equal to 4 times 2, 8. So double exact is just 8. So sysout exact equals plus exact. All right, now using integration, double ds, or actually it's our integral function. So we define an integral function integral function 2D, and it's going to be our func 2D or func, and it's going to be basically this takes var1 and var2 and maps it to 1. All right, so it's a constant term. What's changing is the ds, or element, surface element. Remember so I'm using Cartesian. So 2D integration, and we're going to use Cartesian. So ds is dx dy. So the function f of xy times dx dxy, f of xy is 1. F of xy is basically 1. All right, we only have the dx and dy. And then integral 2D, integral finder Cartesian equals new integral 2D. It takes an integral, a function, okay, but it also takes a domain. So we need to also define the domain. So the domain is define the domain. Now the domain depends on the domain depends on the coordinate system that we choose, right? Domain depends on the choice of the definition of the domain, coordinate system. Why? Because remember, the domain has to give us the information about the bounds of the lower bound and the upper bound of each variable. So we're going to have an integral domain 2D, domain Cartesian new integral domain 2D, and we're going to use an anonymous class. And var1, we're going to assume that var1 is the independent. So var1, it goes from 0 to 4, and var2 is the Okay, var2 mean, var2 max, var1 mean goes from 0 to var1 max is 4, var2 mean and var2 max. And here in the choice of Cartesian coordinates, var2, which is y, is independent of var1. So minus 1 to 1. It's fixed, right? Now we pass in our Cartesian domain. Alright, everything is set. So let's say double result Cartesian equals integral finder Cartesian Gauss-Legendre, and sys out result Cartesian equals plus result Cartesian. Alright, let's run this up. It returns 0 instead of 8, and the question is why. var1 mean, var1 max, var2 mean is from minus 1 to var2 max is from 1. Our function is 1. Alright, and why is this returning 0? Let's see. Let's go to our integral 2D. So in the Gauss-Legendre, we create this function 1D. We call the Gauss-Legendre on this from, so if it runs on var2 first, var2 mean minus 1 to 1. Okay, and then integral function 1D, find 2D value var1, var2, and var2, this is basically 1. So we're integrating over constant number from minus 1 to 1. So let's see, sys out func 1D dot value at, let's say, 2.0. Func 1D equals zero. So the func 1D equals 0. That's because this domain is var2, it should be mean. Alright, so var2 mean, var2 max, var1 mean, var1 max. Let's test it. So func 1D is 2. That's correct, because the func 1D is basically the integral of the constant function 1 over minus 1 to 1, which is 2, and the Cartesian returns 8. Alright, so we are good. Okay, now let's say because our implementation of the 2D integration and higher order integration is very nice and genius, because it's independent of the choice of coordinate system. We should be able to get the same result by integrating over the polar coordinates. Okay, so 2D integration, but the choice now is polar coordinate system. Alright, so in the polar coordinate system, ds is rd phi, okay, and therefore f of r and let's call this theta. So r is our first variable, or it could be the other one, f of r and theta. And the question is which one of these is the independent and which one is dependent variable, and that's a little bit complicated. So it's actually not an easy task to try to integrate this, because we have to establish a relation between the boundaries. So maybe this was not the best case for doing the comparison integration to, because if I go back to the slide here, I have to figure out between the r and theta. One of them should be the free runner or the independent variable, let's say r. So if I look at this domain, r goes from this point, that's the minimum, and the maximum is here, for example. And then I have to figure out at each r what is the value of the theta, and that's a little bit complicated, okay? Now I guess maybe let's create another method, public static, let's call this public. No need to make them private. Test2, and in test2 I'm going to integrate over a circle. All right, so area of a circle, and in polar it's very easy. ds is r, dr d theta, therefore f of r and theta is r, and obviously either of them could be independent variables. So if the radius is r, then we know that r goes from 0 to r, capital R, and theta always goes from 0 to 2 pi. All right, so let's consider theta. Let's consider theta as the independent variable. So double exact, what I'm going to set here, double radius is, let's say, 5, and exact is radius times pi times r squared, right? Math.pi times radius times radius. Sys out exact equals plus exact. So pi times r squared, let's comment test 1, is 78, right? 25 times pi is 78 something. And now we're going to use polar. So our integral function 2D, let's call it func or func1 or func polar, is going to be just maps var1 var2, and let's make sure that we understand the name. So let's call this radius and theta. Give them nice names. This goes to radius, okay? F of r and theta is r, and okay, so we cannot have radius value. All right, so and now what we're going to do, we are going to also define an integral domain 2D, domain polar equals again it doesn't take any parameters, new domain or integral domain 2D anonymous. So we have to choose which one of these two variables is independent variable or free runner. Let's assume that theta. So here var1 I'm taking as theta, okay? So theta goes from 0 to 2 pi, math.pi, and r, so this is radius, var2 radius, and var2 again is independent of var1 of theta. At each theta, radius could go from 0 to basically radius value, and it's complaining cannot be resolved to a variable. Oh shoot, okay, let's just delete test 1. Why am I doing this in so here? So again, var2 is radius, which could be a dependent, but it's in this case it's independent in the polar coordinates. It goes from 0 to radius value. And var1 is theta, and it goes from 0 to 2 times math.pi. Alright, so we have the domain of integration, so we just need to create an integral 2D. Integral finder polar equals new integral 2D, find polar, domain polar. And finally we're going to get the double result polar, integral find polar, Legendre, C-South, area polar equals plus result polar. Let's run this, and as you can see, we do have a so we do have some error here. Exact is 78 pi squared, pi r squared, and the area in polar it returns 98. Why? Let's see. var2 mean radius goes from 0 to that's because, okay, sorry, so that's because here I defined radius as var1, right? Remember, the order here matters, so the order matters. So let's make sure var2 is theta, which goes from 0 to 2 pi math.pi, and var1 is radius, and make sure it goes from 0 to radius val. Alright, this should work. Yes, alright, so we get the same result, 78.5398 163397448, pretty much exact. So Gauss-Legendre with 100 sub-intervals for 1D integration is good. Now let's do Cartesian. And in the Cartesian, the problem is that let's assume that x is independent, and y is dependent. And if x goes, so x goes from what to what? If the radius is r, x can go from minus radius to radius, alright? At each x, y can go from minus square root of 1, or the radius squared minus x squared, okay, to square root of radius squared minus x squared, alright? So here the dependent variable, or the second variable y, the bounds are dependent on the first variable. And what is our integrating function or integral function? So we know that we want to integrate over the element of surface, or surface element, which is dx dy. So therefore f of x and y is 1. Our integral function is basically constant. So integral function 2D, find Cartesian equals, so basically let's call them x and y to emphasize that we choose x as var1, which our assumption was that var1 was the independent variable, goes to 1, okay? And we have to also define a domain, integral domain 2D, domain Cartesian equals a new integral domain 2D, and again anonymous class. So remember, by the definition of integral function, we already established that y should be the variable 2 and x should be variable var1. So var2 is y, which is dependent, and var1 is x, which is independent. It goes from minus radius val to radius val, or plus radius val for a circle, right? And then at each x, the var2, which is y, goes from minus math dot square root of radius val times radius minus var1 times var1, okay? And var2 max is math dot square root of radius val times radius val minus var1 times var1. So our function, integral function, is a constant, but the domain or the boundaries of the domain of integration are not constant. The second variable, which is y, depends on the first variable. Now that we have this, let's just go and create our I think we should be here. Create our integral 2D, integral Cartesian equals new integral 2D. We're going to pass in our fun Cartesian and domain Cartesian, and then double result Cartesian or area Cartesian equals integral Cartesian Legendre, Gauss-Legendre, and then sys out area Cartesian equals plus result Cartesian. All right, we're all set. 78.54. So as you can see, the Cartesian is not as accurate as the polar, okay? And it's also not as fast as polar, because polar, the two variables are independent, the bounds are independent of each other. Okay, but this proves that we can in fact calculate the same integral in two different ways using two different coordinate systems, and it should give us the same result. And the key here is that we have to be able to specify the integral function and also the domain of integration. And the main thing is the dependence of the variable, the boundaries of the domain, the boundaries of one variable on the another. So one of them is a free variable, the rest could depend on the previous ones. All right, so this was an introduction to the higher order integrations or higher dimensional integration. Thank you for watching, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on 2D and 3D integration, and we already discussed about 2D integration. Now let's look at the 3D integration. All right, and the goal here is that, okay, 3D integration, we want to reduce the problem of a 3D integration in its most general form into 3 one-dimensional integration, because we already know how to accurately calculate one-dimensional integration. Okay, and again, one of the variables is always can be considered as the free running variable. In this case, we have x, y, z, and we're fixing the boundaries of x from a to b. So x is our free running variable, which by convention I call it variable number 1. So in my convention, the variable 1 is always defined as the free runner. All right, both in the function, integral function, and in the domain object. And the second and third variables can be a dependent variable. All right, so those can be dependent variables, and what we know is that my convention is that the second variable var2 only depends on the first variable var1, and var3, the third variable, could in fact depend on both var2 and var1. All right, so this is my convention. var1 is free runner, var2 only depends on var1, and var3 only depends on var1 and var2. All right, so this is the most general case. It cannot get any more general than this, right? We have a f of x, y, z, and they could be connected, so this function may not be separable in terms of the x, y, z variables, and the domains are also connecting the variables together. Now we have to convert this into 3 steps, and in each step we want to perform a one-dimensional integration, right? So obviously our function, the three-dimensional function, is a three-dimensional integral function, and then we have a three-dimensional domain. These two are interfaces, and then we have a integral 3D object that takes these two, breaks them into 1D integration, right? So the first thing is that we need to integrate always on var3, because var3, the domain could depend on x and y. And this should return a two-dimensional function, j of x and y. And then we pass this to, and then we do another integration on var2, because the domain of var2, the boundaries could depend on var1, okay? And then this returns a one-dimensional function with a fixed boundary. It only depends on var1, and then we finally calculate this and get a numerical value for our integral, okay? And again, this approach of having var1, var2 depending on var1, and var3, the domain of var3 depending on var1 and var2, gives you a very general case in which you can choose any coordinate system to do the integration, right? It doesn't have to be Cartesian. It could be cylindrical, spherical, or any other coordinate system. So let's head to Eclipse and try to implement this. So we already have this integral project, and we have integral 2D, and we have interface for integral domain 2D. Let's copy these. Interface for integral 3D, we already have implemented this. Function 2D takes two variables, var1, var2. Integral function 3D takes three variables, var1, var2, and var3. And again, remember our convention. var1 is free runner, so this is my convention. My convention is that var1 is free runner with fixed boundaries. var2 only depends on var1, and var3, the boundaries of var3 depend on both var1 and var2, okay? And we have integral 1D, integral 2D. Let's do integral 3D. Integral 3D, all right? Now in the integral 3D, we're going to have a integral function 3D, func, and then we're going to have integral domain 3D, all right? And then we're going to have a constructor, public integral 3D, and here we're going to pass in a function, integral 3D function, and domain 3D object, right? That defines the domain. And then we have to use this keyword to make sure no shadowing happens of the variables. Domain 3D equals domain 3D, all right? So this is the here, and then we're going to have one method, public double. Let's implement Gauss-Legendre. And in the Gauss-Legendre, again, I'm going to use a 5-point Gauss-Legendre. We can do 10 points, doesn't matter. And then in the Gauss-Legendre, what we are going to do is so eventually what we are going to do is we're going to have an integral 1D. So this is the last step. Basically, we're going to write it backward. In the last step, or step 3, which was the integration of qx, right? So in the integration of qx, we're going to have an integral 1D. So integral, let's call it q, function q, and the new integral 1D, and we're going to pass a func q, right? Let's go back here. We're going to, yes, so we're going to pass a function func q, and then we're going to double result. The result is going to be the result of integrating this over, let's call this Gauss-Legendre, and the boundary over its boundary, and then we're going to return the result. And what are the boundaries? The boundaries are from the free runner, right? So the last step is integrating over free runner variable, which by our convention is var1. So we have to get call the domain 3D, get var1 mean, and then domain 3D get var1 max, all right? So min and max of var1. Now we have to create this find q. Now in order to find q, we go one step back. This is step 2. And step 2, this is basically integrating over var2, right? And it returns, should returns a function. It returns a function of var1. So what we have to do here, we're going to make sure that we have an integral function 1d find q, which is equal to var1. It should be a variable of var1, and we're going to use a lambda expression. And in order to do the lambda expression, we know that this find q, this q function is a result of 1d integration over var2, right? So we're going to have here we're going to have new integral 1d find j, and then Gauss-Legendre start and end. All right. And this j function, find j, again we're integrating over var2, so we have to call our domain 3D and get var2 mean, and we pass in var1 because var2, the domains or the boundaries of var2 might in fact depend on var1. So domain 3D get var2 max var1. All right. And so okay, so var2 mean, var2 max, var1. All right, now we're going to go so this was step 2, and one step back we need to define this find j. And again, this j is the result of the integration over the original function, all right, over the third variable var3. So we have to go to actually step 1, integrating over var3, and returns a function of var1 and var2. All right. So what we are going to do, we are going to say that integral function 1d func j equals to so here we're going to say that okay, var1 goes to we could in fact find j. I think we should do a nested so instead of this we should do a nested object. So we have to create this find q, right? And then we know that integral function 1d find q equals var1 to something, right? And that something comes from a new integral 1d of some function func basically we can do this, or we can so another way, instead of having this, q is the result of a double integration, so we can do a double integration. That's one way. So let's try that. So we're going to say okay, integral function 1d comes from the fact that var1 it's going to be a function of var1 and it's going to be a function of var1. All right, and it maps var1 to new integral 2d, right? And in the integral 2d that makes it look complicated. So let's try just nested integral 1d of some function func j with the let's say Gauss-Legendre, and and we're going to integrate over basically var2, right? So domain 3D get var2 mean, domain 3D get var2 max. Okay, and let's put the semicolon here. So what we are doing here is but then the question is this func j, how do we implement this func j? Because this func j is supposed to be depending on var1 and var2, right? So what we are going to do, we're going to use another lambda expression inside here. So here we're going to say that this function maps var2 basically to something, to the result of an integration. So new integral 1D of some function which was our func 3D, func value var1, var2, var3, right? Let's see again. So we want to calculate this. So we need to first find qx, and qx is the result of integrating over var2, okay, over func j, integrating, yes. So here we're defining func j, and func j is basically the result of integrating our function over var3, okay. So here what we're saying here is that, okay, var2 maps to here, integral function, and this function requires map3 func dot value var1, var2, var3, and the construct is ambiguous. So I guess here in this integral 1D, let's first comment this out. Guess here we also get some problem, but let's also comment this out. All right, so we don't have the ambiguity anymore. So let's see what we're trying to do here. We're trying to do some nested integration, all right? And var1, so func q is a function of var1. So we're mapping var1 to the function. That function is the result of integrating one-dimensional integration over var2, okay? But the second function also depends on result of integrating over var3, which is the original function. So what we do here, we call the Gauss-Legendre. Let's just see, so we are integrating over var2, and now we are integrating over var3, Gauss-Legendre, and we want to do the, okay, so let's add the start, domain 3D dot get var3 mean, and then domain 3D get var3 max, var1, var2, var1, var2. So it's just a little bit of nested code, nested integration. Okay, so what we are doing here is that we're mapping var1 to the function for function q, and that one is the result of integration over var2, and that function also is the result of integration over var3 from the original three-dimensional function. So we integrate over basically we integrate over original 3D function, okay, on the domain of var3 min, var3 max, and it returns this basically becomes a function, a value that depends on var1 and var2, and then we integrate over var2, okay, on the domain of integration, basically domain var2 min, var2 max, all right, and then it becomes a function of var1, and then we again integrate it over var1, and this should work. So let's go ahead and try to test it. Integral 3D, test integral, new class, test integral 3D, okay, and let's have a main method here, and in the main method I'm going to have some method called test1, and let's just generate it. In test1 I'm going to get the volume of a sphere, and in order to do that I'm going to use a spherical coordinate system. The reason is that when I choose spherical coordinates, dv is dx, dy, dz, right? But then the problem is that the boundaries are kind of complicated. So if I use Cartesian dx, dy, dz, then my function is very simple. F of x, y, z is 1, but domain is complicated. Okay, so in the spherical coordinate, dv is r squared sine of theta dr d theta d phi, okay. So my function is still function of r, theta, and phi is r squared sine of theta. It's not complicated, but the good thing here is domain is very simple. Domain is simple because what happens is that in a spherical coordinate, in order to cover the whole sphere, r goes from 0 to the radius, and theta goes from 0 to pi independent of r, and phi goes from 0 to 2 pi independent of r and theta. So all the domains are independent. And that's the whole point of changing coordinate systems, because we always want to work with a coordinate system that makes the domain very simple and, if possible, independent for different variables. That's always the choice, because that shows the symmetry of the problem. So let's do a spherical coordinate system. So what I'm going to do is that I'm going to define an integral function 3D func, which is mapping var1, var2, and var3. And again, because in the spherical coordinate the domains are independent, it doesn't matter which one is the free runner, okay. So let's assume that radius is the free runner, and then theta is var2 and phi is var3. But remember, our convention is that var1 is free runner always, var2 is only depending on var1, and var3 only depending on var1 and var2. So here my function becomes radius times math dot sine of theta, okay. So this is my function, and now the domain, integral domain 3D, new integral domain 3D. So let's just use an anonymous class, and in the anonymous class let's start with var1. So var1 is radius, and let's also define our exact value, because this is the problem that we already know the solution. So double radius value is, let's say, 5, and then double exact is 4/3 times math.py times radius. Let's just use the power function, math.power radius val to the 3, and sys out exact equals exact. All right, so that's the exact value. So var1 is radius, it goes from 0 to radius val. Okay, var2 is theta, it's independent of the domain, is independent, it goes from 0 to pi. And var3 is basically is phi, and again its domain is independent. In this case, in the spherical coordinates, it goes from 0 to 2 pi. All right, now we have our integral function and domain of the integration in spherical coordinates. We need to create our integral 3D integral finder, or integral spherical equals new integral 3D, find domain 3D, and double result spherical equals integral spherical Gauss-Legendre, and sys out result spherical equals plus result spherical. All right, so let's test it. And as you can see, the integration took quite some time, but it returns the exact result, right? 523.598 7755 98299. All right, so Gauss-Legendre worked, but it was pretty slow. As you can see, I'm running it again, and it's thinking and thinking and thinking. Yes, and the reason is that so we're doing this nested integration, and what we're calling is Gauss-Legendre method, and in the Gauss-Legendre we're using 100 subintervals. It might not be the best case. Maybe we probably don't need 100 points, 100 subintervals, and that's what's limiting the performance, right? And then the question is, let's try to do, for example, Simpson. So instead of Gauss-Legendre, I can implement this for integral 3D with a different method. Let's say Simpson, all right? And again, the code is exactly the same. Ctrl+Shift+F to format it. And the only difference here, instead of Gauss-Legendre, I just call Simpson method start end. All right, and in the Simpson we need to also specify how many subintervals. Let's say we only say 100. Let's say 50. Or let's keep 100. But Simpson is probably faster than the Gauss-Legendre. Simpson, and then we're going to have 100, and instead of Gauss-Legendre, Simpson, and then we're going to have 100 again. All right, so in the test here, instead of having Gauss-Legendre, I'm going to call the Simpson method. Simpson. Okay, now the Simpson is pretty faster than the Gauss-Legendre, but it still gives a pretty accurate result. 577. So we have 598, 775. So it has about 60 decimal places of accuracy. All right. So this was the 3D case, and now we can do basically some advanced vector calculus using this kind of integration. Okay. Now what happens if we decrease the number of terms here? For Simpson, let's say 50, and then still fast, but we're losing some accuracy here. Okay, and again, this accuracy, we still have like 5 decimal places of accuracy, which is good enough. Okay, and if I wanted to do this calculation basically in Cartesian coordinates, it was kind of difficult. But let's try to do this in cylindrical coordinates. And for cylindrical coordinates, things are also not that easy, because the boundaries, again, the problem here is calculating the volume of a sphere, and because of the spherical symmetry of the problem, it's always recommended to use a spherical coordinate system. Okay, now you can try to find the volume of the cylinder, and in that you will find that, okay, because of the cylindrical symmetry of the structure, we should use a cylindrical coordinate system. All right, thank you for watching. I hope you enjoyed this, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to talk about one very interesting thing about numerical integration. So far we have discussed 1D, 2D, and 3-dimensional integration of functions, and now one question that remains is this. Assume that we define an integral function. So f of x is a given function, and we define g of t, which is an integral function for f, which means we are integrating f from some initial value a for x times some variable t. All right, so if I want to find the value of g at some point, I have to integrate f of x from a to that point. All right, so this is called the integral function or antiderivative. Then we already know that the fundamental lemma of calculus for one-dimensional function is that if g is an integral function of f, then d dt of g equals to f of t. All right, so g is antiderivative. So if we take the derivative of g, we should get f. That's the thing. But then the question is, all right, g is defined as an integral of f. So how to find the g of t over an entire interval from a to t1? So I want to find, for example, g at 1000 points inside this interval. Obviously, option 1, which is the naive option, is to just simply, for each value of t, we do the integration from a to that value t. All right, for each t. So if I want to get the value of g at 1000 points, I have to do 1000 integrations. All right, so that's not a big deal. We have to kind of do it at the end. But the problem is that if t is very large, let's say this t1 end of interval is very large, then when we get to the last points, then the interval becomes very large. That means that we have to increase the number of subintervals. If you recall, in the integration, for any method that we did for numerical integration, we said that we have to divide the original interval into subintervals, and in each subinterval we do Simpson or Gauss-Legendre or Newton codes, interpolations or quadrature rules. So if the end of interval is very large, then for the last points, let's say 100 last points, if I am calculating 1000 points, the cost is become very large, right? The cost of integration. Now the second option is that, okay, instead of doing numerical integration, I numerically solve this differential equation, and that's also an option. And remember that for any first order differential equation, we need an initial condition, and based on this definition, we know that if g is evaluated at a, then we are integrating from a to a of f, and integration of a to a is always 0. So the initial condition is g of a is 0. But then the problem is that this is not a nice way of doing this, because we are actually changing the problem that we're trying to solve. The problem is to calculate this integral for 1000 points in the interval of a to t1. Even if the t1 is very large, we want to do this calculation for 1000 points very efficiently. All right, but we are changing the problem and saying, okay, go and solve the differential equation. That's one thing. So we do not want to change the problem. The other thing is that solving differential equations using higher order approximations is usually costly if we want to get good accuracy. All right, so what we want to do eventually, we want to stick with our simple integrating approaches, Gauss-Legendre, Simpson, these kind of very simple approaches or methods. But we want to be able to efficiently calculate g over very large intervals for many number of points, let's say 1000, 2000 points. So what I'm going to do here, I'm going to introduce a third option, which is called memoized integration. So what do I mean by memoize? So memoization is a term which we usually hear in computer science. And I've taken this definition from Wikipedia. So it says that in computing, memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls and returning the cached result when the same inputs occur again. So how do we apply this to, for example, our problem of calculating the g of t in 1000 points over the interval? Is that we use the breakpoint property of integration. So let's say I calculate the g at some point t1, all right? And then now I want to calculate the g at another point t2, where t2 is greater than t1. So I can write the integral of from a to t2 as a sum between a to t1 and t1 to t2. Now t2 could be very large, t1 could also be very large, but t1 to t2 could be very small or small enough, right? So if I already have calculated the integral from a to t1, in order to calculate the a to t2, I store the result of the integral a to t1 at somewhere, and then I only add the result of integration from t1 to t2, from t1 to t2 to the previous one. All right, so when I start to do if I want to calculate g of t at 1000 points, I start from the first point and then second point, third point. For example, for the fourth point, I only calculate the integral of f from the third to fourth point and then add it to the previous result. All right, so this way we are very efficiently, and the key here is that to make sure that the difference between the two steps, t1 to t2, from t1 to t2 is small enough so that we can just simply apply a Simpson method or Gauss-Legendre quadrature method. Okay, so this way we keep the accuracy regardless of how big the interval is. We always keep the same accuracy in all the steps in calculating the value of g at each t point, at point t, right? Because the only thing that we're adding in each step is this extra integral, which is the interval is very small. All right, and we can use a data structure in Java such as list or map for memoization, for storing the results. So let's go to Eclipse and try to implement this memoization technique for integral. So we have this demo integral, and here I'm going to create a new package. Let's call this memoize, and here I'm going to create a class memoized integral. Okay, here obviously we have an integral function 1D func, that's our function f, and we need to import this. And then we have a constructor public memoized integral, and let's call, and the input is basically the same. We just pass in the function and also double start. Okay, so we have to also know what the start point is, double start, and then this dot func is func, this dot start is start. All right, so how do we implement the memoization? So we can, first of all, we can have a setter for, so public void set start double start, this dot start equals start. Okay, so and we're going to have a method public void calculate, or yes, calculate, and then what we want to do is we want to have int number, num points, or number of points, okay. So we want to say, we want to let the user set the number of points that he or she wants to calculate the function at over the interval, right? And okay, maybe also we need to have an end, so we have to specify the entire yeah, so we can specify the entire interval, or we can specify just here. And okay, let's specify it here. So double end and integer number of points. Okay, so what we want is but again, because this is an object, it's going to store the data, so it's better that these parameters don't have any this method don't have any parameters. So and then we're going to have a setter public void set end double end, this dot end start end equals end. Okay, and then we're going to have an integer number of points, and we're going to give it a default value of 100. Okay, and then we're going to have a setter for it, public void set number of points, int number of points, and this dot number of points is equal to number of points. All right, so this is the assignment. And okay, so we can also remove these, because then the user can just use the setters to do it. But okay, so let's just focus for now on the calculation. How do we do the actually implement the memoization? Implementing memoization. So we're going to create an array. So let's say let's use hash map, for example. So map integer and double, let's call this cache. So we're going to do the caching. Okay, and let's import the map from Java util. So we're going to create our hash map in the constructor, for example. So cache is new. I'm going to use a hash map, and it's automatically going to infer that. We actually don't need this, right? Because it's going to automatically infer the type, but let's just keep it. Okay, and then we have the cache, and the cache is originally empty, so empty cache. So what we are going to do, we're going to break the interval into some points, right? And based on the number of points, we're going to do the integration. All right, and let's say that we want to have the okay, so delta, let's define our delta. Double delta is basically end minus start divided by number of points. Okay, and then what we are going to do for int I equals 0, I less than the number of points, I plus plus, we are going to do the integration. All right, and then basically so integrate from basically let's see, double t start, or maybe let's call it t1 is start plus I times delta, double end, or t2 is basically start plus I plus 1 times delta. Okay, and so this should be okay, that's correct. And then what we want to do, we want to integrate over t1 t2. So the result, so here we want to, this for in each step in this for loop, we are calculating, integrate over the start to the value t, okay, which is t2. This is the end. Okay, t, let's call this t. And then what we want to do, we want, if instead of integrating this, what we want to do, we want to basically only integrate, basically the result in each step should be the result in the previous step, right, from start to t1. T1 is one step before t, and okay, let's maybe remove this, let's call this I, or I plus 1. Okay, so, and plus we just integrate from t1 to t2, let's call it t2, doesn't matter. Okay, so we just want to do this, and we're going to add the result, our cached result from the previous step. But in order to do that, we're going to test. So if cache contains key, let's say I, if index I is available, which means we already have calculated this from start to t1. So we just say that, okay, double result is basically cache get I, right, result of previous step plus new integral 1D, pass in our function Gauss-Legendre from t1 to t2. Okay, so we're just integrating from t1 to t2. And the thing is that we don't want to, so in this Gauss-Legendre, we're dividing by 100 sub interval, which defeats the purpose. So what we are going to do, I'm going to call, for example, Gauss-Legendre 5 point, t1, t2, all right? I just do the 5 point without any subdivisions. So this is the result. Now we get the result, we're saying that, okay, and now we need to put this back into the cache. Okay, so cache dot put index I, the value is the result. So that's our cache. So if the cache doesn't have index I, which means the index I has not been calculated. So what we are going to do, we're going to basically calculate it. So the same thing, but here the integral goes from 0 to t1. Okay, so that's how we calculate the cache. And let's double check, see what's happening. So we start from I0. Okay, at I0 t1 is a start, t2 is a start plus delta, and then the cache is empty in the beginning, so we go here and we calculate from 0 to from start to t1. Okay, which is basically 0. Actually we should calculate from t2, or t1. Okay, so in the beginning it's 0, right? From, if t1 is the beginning of the interval, which is a start, so integral from start to start is 0. So so then for I0, which is the start point, the result is 0. We put it there, and then we go to the next step, which is I equals 1. t1 is start plus delta, and t2 is start plus 2 delta. So I guess then we check if cache contains 1. Actually this get should also be I minus 1, right? So what we are doing here is so at I0 actually when we have the previous step is I, so the next step is I plus 1. all right, so if I is 0, we have a start plus delta, and then so I is the current step, so we have to look at I minus 1. We put I. So if I is 0, we go here, we put I. Okay, correct. And then I becomes 1. t1 is start plus delta, t2 is start plus 2 delta. So I guess this should be I minus 1 and I. And then I is 1, start plus delta, cache contains 0, correct, so we get the result from previous step, and then we integrate and we put it there. Now both of the results of I equals 0 and I equal 1 are in the cache, and then I becomes 2, start plus delta, t2 is start plus 2 delta, cache contains 1, so we go here, we retrieve it, plus we integrate from t1 plus t2 and put the value of 2. Okay, all right, so this works, so this caching works. And then we can also have an array, so public double, for example, get result or get results, and here we can convert the map. So we can say double values or result is new double number of points, and for int I equals 0, I less than number of points, I plus plus results I dot results I equals cache dot get I, and then return results. Okay, Now we can go and test it. So test class, test memoization. We're going to have a main method here, and here I'm going to call test1, and let's create test1. In test1 I'm going to have integral function 1D, and let's call it func, and here t goes to t sign up math dot sign up t. Okay, we need to import this. Okay, and then we're going to have a memoized integral, memo new memoized integral func, and then we're going to start from, let's say, 0 to 200. So that's a fairly large interval from 0 to 200. Okay, and then what I'm going to do, I'm going to try to plot it. So MATLAB chart, fig, new MATLAB chart, and then fig.plot xy. So what I'm going to do, these are the results, and public double get points, and for the points we just do a for loop, double x or points, new double number of points here, and then delta is this for int I equals 0, I less than number of points, I plus plus points I equals start plus I times delta, and then we're going to return points. Okay, and then x, so x is memo get points, y is memo get results. Okay, and then after we create the memo we have to call the calculate, and then fig dot render plot, fig dot show. Okay, now I need to go to the run configuration, and in the arguments I have to uncheck this, and that's a bit odd that we didn't get anything. Why? Let's uncomment this. Maybe let's plot 2, for example. Let's see. Still nothing. N minus start over number of points. Okay, that's because we're dividing by, okay, these should be double. We have to be careful here. Still nothing. Let's see. All right, let's look at the values. So sysout arrays to a string of some to a string memo dot get points. So let's check if the points are correct. Okay, so that's because everything is 0. I less than number of points. Why is everything 0? Points I is start plus I delta. So that means delta is 0. But why is delta is 0? Because we forgot to initialize the end. Okay, so now it works. All right, from 0 to 1.98, and the problem is that the 2 is not included. So what we need to do is okay, so let's try to plot it one more time. Yeah, that looks let's maybe try to do t. So t is linear, so its integral function should be a quadratic. At 0, at 2 we should end up with the so the integral function is t squared over 2, so we should end up with 4 over 2, 2. That's correct, right? At 1 we should end up with 1 over 2, which is 0.5, right? Now the thing is that here I can increase to 20. At 20 I should end up with 20 squared, which is 400 over 2 is 20, and it was still pretty fast. Okay, and so, and then let's go 200. At 200 I end up with 40,000 divided by 2, it's 20,000, and it's pretty accurate. Okay, now let's try to do this without memoization, and recall that with memoization we're getting a pretty fast result, right, over this large interval. If we didn't do memoization, so private static void test2. In test2, what I'm going to do, I'm going to just do naive integration. Naive integration is that, okay, we have the same thing here. We're going to plot the stuff, but we're going to have double x is basically math utils linear space from 0 to 200, and we're comparing with 100 points that we had, and then double y is basically new double x dot length, and then for int I equals 0, I less than x dot length, I plus plus. What we are going to do, we're going to say that, okay, yi is the result of integrating of our function from, and remember in the memoization we're using 5-point Gauss-Legendre, right? So let's exactly do that again. Gauss-Legendre 5 points, and the start is basically x0 to xi. Okay, so this is the naive integration. We're just integrating from a start point to the sum point inside the interval that we want to have, and we want to have 100 points. So we're doing 100 integration without any caching, right? And then we're going to plot it. So everything in these two cases are the same. So let's see. It still works fine, right? And what we see here is that it wasn't that, so let's also add timers for the integration for the whole thing maybe. So timer, timer, new timer, timer dot start, and then we're going to do timer dot stop and timer dot show. For both cases here. Actually, I'm going to put it after. Okay, yeah, maybe just everything. So the naive test 2 is the naive approximation 48 millisecond. Let's see test 1. It's 50 milliseconds. So in this case, it's really not that much of a difference, right? But if we increase to 2000, for example, here. So running test 1 with memoization. Maybe run both of them. Memoization 48, and then the non-memoization is basically 1 millisecond. Let me see why this happened. So if we just run test 2, it's 48 milliseconds. So there is some delay because of just launching the application, setting things up, right? Loading the class into the memory. But there is not much difference in this case between test 1 and test 2, which means with memoization and without memoization. But there will be many cases that maybe let's just change the function to something more t times math.sin of t. This is our, let's make this as our final comparison, math.sin of t. So first thing is memoization, 50 millisecond, and again I changed the function, but the duration didn't really change because caching, putting things in a hash map and retrieving it back is a constant time. It doesn't really depend on the basically the interval or the function that we're using. So 50 millisecond for test 1 with memoization. Let's see how much. 48 millisecond with but you see the problem here, right? Without memoization, the problem here is that this is wrong, right? Because we're doing 100 points, but the problem here is that when the interval becomes very large, 0 to 2000, so around here, with only 100 sub-intervals, we cannot have a good approximation. That's the main problem. And in order to increase it, increase the accuracy, we have to go 1000. So let's do this. So memo.set number of points 1000. And again, 1000, it still does maybe. Okay, so let's reduce the interval to 200, but we're testing with 1000 points. It takes maybe let's just reduce the interval to 20. So we're doing 0 to 20, but with 1000 points. And this is without memoization, with memoization. Okay. Now what's showing here is that there is something going on, right? Because let me see, we have -2, this goes up to 35, this goes up to 16. So there's definitely something different between the two, right? And so in with memoization we get this function. Without memoization we get this function. So let's compare them. Yeah, for small ones it seems to be correct. At 12 it's -15. Here we get about here we get about -14. Here we get about -12. So one of these is not correct. So let's see, let's increase the value here to 2000 points, and we're running test 2. It still seems to not change much. So let's try to do the here 2000. Now it seems to be similar to the previous result. Okay, and as you can see, basically the time for memoization doesn't really change that much, because even if the interval is very large. Let's go 200. The result 54, and now let's try test 2. 52. And you see the problem, right? So this is with memoization and it's the correct result. Without memoization, you see it's all incorrect for right around here, right? We definitely don't get a good result. So in order to get a good result without memoization, we have to increase the number of points, 5000 for example. And again, it still doesn't work. 10,000 points. Still not good enough. 20,000 points. Still not good. So there seems to be, let's say 100,000 points. No, it still doesn't work. So in this case, because the interval was very large, this naive approach completely failed. We cannot get any good result. And but the memoization gives us a very nice good result, and it's pretty fast. So with 2000 points we're getting about 50 milliseconds, 56 milliseconds. With 5000 points we get about 60 milliseconds, and it's pretty fast, pretty accurate. This is the most accurate result, okay, for integrating the function. All right, thank you for watching. I hope you enjoyed this, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue the discussion on numerical integration. In the last lecture, we talked about memoization of integration. What it meant was that if I'm trying to calculate the integral function of a given function f, so I'm basically trying to calculate the integral from a to some point t. I want to calculate at different t's, right? So g of t is the integral function of f. And we said that a very good approach and a very fast and accurate approach is to use memoization. It means that if I want to calculate at some point t2, calculate this integral, and I have already calculated from a to t1, where t1 is less than t2, I can reuse that value and just only calculate the integral from t1 to t2. And if this delta t, basically distance from t1 to t2, is small enough, I can use a 3-point or 5-point Quadrature, Gauss-Legendre method, to calculate this extra integral accurately, and then add the previous result to get an accurate result for t. And this helped basically get rid of the problem with the fact that when t goes very large, let's say t goes 100 times a, right? Then numerical integration, if we directly try to numerically integrate that large interval, we have to have a lot of sub intervals, which is not good. But this way of doing the calculation takes care of that, because we always just do the integration over a small interval and add it to the previous one. And the point here is that we want the value of g at all those points, not the end of the interval, all the points, right? And one good example is calculating convolution integrals. So a convolution integral appears all the time when you're studying linear time invariant systems, usually in linear control theory. So in the control theory of systems, convolution happens all the time. And it's basically based on the idea is that if I have a LTI system, linear time invariant system, I can characterize it with a function called impulse response. So this g of t, it's the impulse response, and it's the characteristic of the system. It doesn't have any relation to the type of input that we put. And if I know the g of t, the impulse response of the system, then the output of the system to any given input f of t is the convolution of f of t with g of t. G of t being the impulse response, right? So f is the input, g is the impulse response, and f of t convolution with g of t is the output of the system, or the response of the system to the input f. All right? And that's defined by this integral, minus infinity to plus infinity, f of y, g of t minus y, dy. So y is a dummy variable, is the variable of integration, and g is the output. So this output depends on the variable t. So in this integration, t is fixed. We are integrating over y. And this, we can also write this in another form, in which f, the argument of f is t minus y, and the argument of g is y. And we are integrating over y, right? Both of these are equal, and they are basically the same definition for the convolution, okay? So if we have this LTI system, and if I know the impulse response, then I want to find the value of the output over time interval, from time 0, for example, where I input the f of t. Let's say I apply f of t at time 0. And then I want to plot the response from 0 to t0. Let's say I want to find the value of the output, or this convolution integral, in 1000 points from 0 to t0, okay? So the naive approach again is that for each t, we calculate the integral, we do a simple integration. The professional approach is that, okay, if I know the value of output at some point t, then the result is at another time step is the previous step plus some additional term, right? So we use memoization technique for fast and accurate evaluation. Now, an example that I put here is the low-pass filter. So a low-pass filter, when we talked about filters, we typically present them in the frequency domain. So if we take this impulse response and calculate the Fourier transform of it, and this is just the magnitude. Low pass filter is pretty much flat up to some frequency, and then it starts to decay, all right, in frequency domain. In time domain, before t0, when we have before t0, it's basically 0, g of t0, and after t0, it's an exponential function, all right? and e to the minus t over tau, and tau is the time constant of the system, which is related to this flat bandwidth, flat frequency, right, this edge. And the amplitude of gt, so at t0 gt should be how much should it be? I believe it should be tau or 1 over tau, one of these two. And then in order to test for that, we can just look consider the Fourier transform of this. So Fourier transform of e to the minus t over tau times the unit step, because this is 0, it's 1 over j omega minus 1 over tau, right? Or 1 over j omega plus tau, plus 1 over tau. So it's and then if we want this to be normalized, so let's say the frequency response is normalized at 0 frequency, we get 1. So at therefore at time 0 we should get tau. Okay, so the amplitude of the response is tau. So the function is tau times e to the minus t over tau. Okay, so that's our impulse response, and it's 0 before time 0. And then let's say we want to calculate the step response, which means I want to put a step from 0 to 1. Okay, and therefore f is 0 before time 0 and f is 1 after time 0. So if we put, if we use this one for calculating the output, the convolution, so if y is greater than t, it means that the argument of f is negative, which means f is 0. So the upper bound is limited to t when we are integrating over y. And then g of y, if y is less than 0, g is 0. So the lower bound is also limited by 0. So the output response for the step response is integrating of g, just the impulse response, from 0 to t. Okay, and the output is a function of t. So this is exactly the way what we talked about in here for memoization. So right, we're calculating the integral function of the impulse response. And note that if f was some other function than constant, it doesn't matter. The bounds of the integration are still 0 to t. But we get g of y times f of t minus y, right? For y less than t, or when the argument of f is positive. Okay, but here we're just considering the step response. Now let's go and try to implement this in Java. And in our demo integral project, we already have this memoized integral that takes care of memoization. Note that the default number of points is 100. And what we are going to do is I'm going to create another class called low pass filter, for example. Let's have a main method here, and so what I'm going to do, I'm going to create a function that represents the low pass system. So function or integral function 1D G, or impulse response or impulse new, or here. So T goes to what? So we have to have a kind of like an if statement here. So T goes to if T is less than 0, we're going to return 0. So if or we can use the T less than 0. we're going to return 0, else we're going to return math dot basically xpov minus t over tau. Okay, and now double tau, let's say 1 second, so the units are second. All right, and this is our impulse response. If t is less than 0, we return 0, otherwise we return, and we can even plot this. So MATLAB chart fig, new MATLAB chart, fig that, so double time is mathutils dot linspace from 0 to 100 seconds with 1000 points, and double y, for example, is array func dot apply t goes to impulse dot value at t. We're going to apply to time array, and fig dot plot time y, fig dot render, fig dot show. All right, so I should also multiply this exponential by tau, and let's go and remove this check. Okay, so as you can see, tau times minus t over tau, and okay, so it returns 0, so let's go minus 5, for example, to 100. It's just okay, so oh sorry, this should be the value at t, not tau. Okay, so this is our impulse response, and the reason that we're not getting 1 because our resolution is not good, so maybe let's just go 1 to 50, minus 5 to 50, 10,000. Okay, so this is our impulse response. Okay, and as you can see, this tau, if you're familiar with this linear systems, tau represents the width of this pulse. So at 1 second we are about half, more than half. The width of this small pulse reduces. Okay, so this is our impulse response, and then we create an integral function 1D input is t goes to, if t less than 0, we return 0, else we return 1. So our input is a step, let's call it a step input. All right, and I can also plot that y input, let's just call it input, and then we want to plot it, input with the color red, for example. okay, not the input, we have to have a step input here. Okay, okay, let's see. Oh, okay, so why do we have this error here? All right, so we have this. Okay, so the red is the input, which is a step, and the blue is the characteristic of our system, which is the impulse response of the system. Now the output is basically the convolution of these two things. So we're going to have use a memoized integral object, okay, and so we're going to create an integral function 1D and convolution function t goes to t goes to what? T goes to t goes to, actually we shouldn't do this. So what we want to do, we want to create a function and we want to pass in. So first of all, we can directly test the step response, and in the step response we know that we just have to integrate over the impulse response. So let's go and do create a memoized integral out step, new memoized integral. Our function is basically impulse, start is -5 and end is 50. All right, and for this function we set the number of points to 10,000, and then out step calculate. Okay, we do the calculate and we come here and we plot, let's say with green, from out step dot get points, which are the timestamps, and out step dot get results. Okay, so this green. So as you can see, what happens here is that as we expect, we get some sort of rise time, and eventually the response, this green one, which is the output, reaches the steady state, which is basically the output becomes equal to the input 1, but with some sort of rise time, this exponential rising of the function, right? And that's the main characteristic of the step response of a low-pass filter when we calculate the convolution. Now this gives us a very exact and stable result for the output because we're using memoization, so it's pretty fast and pretty accurate, and even if we increase the number of points here, it doesn't really change the efficiency that much. It's still pretty fast, okay, and pretty accurate. So memoization is a great technique when you want to deal with these linear systems, and this topic we will come back to this topic of linear systems and try to study them in very much details. Okay, now what if I want to calculate the implement the generalized version of convolution? So what we can do is let's say for convolution, what we need to do, and we want to use this memoized integral, right? And this memoized integral requires an basically integral function, right? And this integral function So we can write this down out a step like convolution. And what we are going to do here, this impulse, basically the output is the input. Remember this memoization technique, what it does is it calculates a function of t, okay, of a function f. When we're dealing with convolution, basically what happens here is that remember because the signal is 0 before time 0 and the impulse response is also 0 before time 0, what happens is that the boundaries of the integration always go from 0 because of this g to t because of this one, right? So it always goes from 0 to t, and we are here basically, okay? But then the problem here is that there is a t also inside this integral function. How do we deal with that? So we're integrating 0 to t of f of t minus y gy dy, right? And the way that the question is, can we just use this simple memoization object to do that? So this should be y, right? And this should go to like the for example step input dot value at t minus y times the impulse, for example value impulse dot value at y, right? But then we have this problem of t here, so I guess we cannot just directly use this memoized integral to deal with the fact that there is also a t variable inside, right? So what we can do is we probably can update this such that the memoization works for an integral of a to t for a function of f of x and t, okay? So t could also be inside the integration, and the way we are going to do it, maybe we can just so if we pass in an integral function 1d, then we can assume that the input function is not dependent of t. If we pass an integral function 2d, okay, then we can assume that this function also has a dependence of t, right? So func, and let's call this let's refactor rename it func 1d, and let's create a function 2d func 2d, and what we're going to do here, we're going to basically let's see, we're going to assign the func 2d here, and func 1d is null. So then in the calculate we can check. So we're passing in a func 1d, and if the func 1d is not null, which means we already passed this integral 1d object, so the assumption here is that then the function that we are integrating over is not dependent of the t variable. But if func 1d is null, it means that we have supplied a func 2D, so it already also depends on t, right? And what we can do then is to think about which variable, the first variable or the second variable, is the t or the x. Okay, one of them is x, the other one is t. And what we are going to do here is that we're going to assume that the second variable, so here we're going to assume that f is f of x and t, and here we're going to assume that our function f is just f of x, so no dependence on t, no dependence on t. This has in fact dependence on t, okay? Because when we're calculating the integral, it's actually important to know that, okay? The convolution t actually appears inside the integral as well, and that's the main thing. And then when we come to memoization, when we're calculating the integral, we say that basically our x goes to basically we can just test. So this is func 1D, and if func 1D is not null, which means we have set the func 1D, and we assume that it doesn't depend on t, and else if func 2D is not null, it means that actually the func 2D has been set, and our integrand, the function f, depends on t, and t is the second variable, okay? So, but the problem is that we cannot pass in a func 2D, right, in the integral 1D. So we say that, okay, we are integrating over x, func 2D value, and the first variable is x, the second variable is t, and remember t is basically our points, right, that we are integrating, and at each step we are passing calculating from 0 to t2, okay? And here this integral 1D, so we have to calculate at t, and so this should be t2, right? Because in each step the result is the result of integration from start to t2, okay? And this looks good, and the initial condition is that, okay, from start to start is always 0, right? So we just put 0 in. Alright, so let's test our previous case. Okay, still works, and let's try to implement it using a 2D implementation here. Let's say we want to pass in x and t, pass in a 2D function, 2D integral function. It goes to impulse at basically value, and just x, right? So what happens here is that our integrand does not depend on t, but we're using the second construct. So let's see if this works. Yeah, so it still works, okay? Exactly the same result, but using a 2D integral function, which does not depend on the second variable, which is the t, the output variable. All right, so we have this. Now let's try to implement the general convolution. The general convolution, we pass in a y and t to the integral function, and then the step input, let's call this just the input. So let's refactor rename it. It's just the input, and we calculate the input. Oh, okay, so we had this input, let's call this just, I don't know, x. Okay, and then let's do the so this is the convolution, and input value t minus y times impulse at y. All right, so everything is correct. Let's call it out, or just the convolution. So this is a more general case. We're still calculating the step response, but we are using the convolution. Okay, and let's see, why do we have an error here? Oh, okay, so we have to also do the convolution, set the number of points 10,000, and convolution dot calculate. Okay, and result. Yeah, exactly the same result. But then the thing is that now we can calculate the response to the time response to any input, not just the step. So let me just add some parameters here. After rendering the plot, let's say fig.x label time, second, and y label, fig.y label function, and okay, let's run this again. And I'm going to just plot the result of the convolution. And let's copy this and put it in our slides. All right, or maybe let's reduce the interval. So instead of having -5 to 50, let's go -5 to 10, for example. Let's plot it with a blue color. All right, fast configure. Let's copy it and paste it. Here, for example, and let's put the response on top of it. Okay, so this is our time response. Okay, a step response, and what is important here is that so the other thing is that instead of copying, I can save it as a PDF file, and when I go to my PowerPoint, I can directly import the PDF file, so it has a higher resolution, higher quality. So what's important here now? Let's look at other things. Instead of having the step response, let's look at, for example, okay, let's bring this back. This is green. But instead of having a step input, let's go and do something more interesting. So let's say for t less than 0, it's 0. For t greater than 0, let's say we have t, a linear ramp. Okay, this is a ramp input. The input is a ramp function, and we want to calculate the output from -5 to 50. And so the blue one is the step response, the red one is the input, which is the ramp, and the green one is basically the response. Let me just double check. So input t minus y, and impulse at y, yes, and then we are calculating the convolution from -5 to 50. Input t minus y, and then output impulse dot y. Yeah, that's correct. And let's say this is, for example, math dot sine of t. So we have a sinusoidal with frequency of 1 Hertz. And so so again the output is something like this. So let's reduce the frequency. The green one is the output. Okay, this was an interesting topic about how to efficiently calculate a function over a long interval using memoization. I hope you enjoyed this, and I'll see you in the next video. Hello and welcome to another Java tutorial. In this tutorial, I'm going to look at the other good libraries for numerical integration in Java, and one of them that I highly recommend is the one from Michael Flanagan library. And it's just you search his name, Michael Flanagan, and he's a professor at UCL, University College London. And in his project flanagan.jar, you can just download the Java archive file from his personal website. There is a package called integration, all right? And basically we can divide the classes in this package in 2 parts. The first part is just numerically integrate a real valued function, all right? And very similar to what we did, it has an integral function interface. Now what we did actually was to divide an integral function interface for 1D functions, and then 2D functions and 3D functions. And then it has a class called integration, similar to what we had. So we defined the class called integral 1D, which integrated with different methods for one-dimensional functions. So this part, so there is this integration class, and then there is this integral function interface. So this part has an interface for defining function and a class for performing various integrations. And the part 2 is for solving differential equations, a system of ordinary differential equations. It has a derive function. So if you want to solve y prime equals f of x and y, and we will look into the details of solving differential equations later in the course, but for now the deriv function is basically for solving y prime equals f of x and y. So the deriv function is an interface for implementing this f function. The deriv n function, so there is an n here, is when you have a system of n equations like this. So y prime of 1, y prime 2, y 3 prime, etc. equals f of x, y1, y2, etc. So you have n functions and n equations that define the first derivative of those n functions, which gives you n equations. So two interfaces for defining your system of equations, and one class called Recursive, which solves the differential equations using different methods. The most notable one is Recursive method, okay? And it's more like a fourth order interpolation of your differential equations, which is basically based on Richardson extrapolation, okay? So let's head to Eclipse and try to look at these two classes. So if you go to my MathLib class, in the referenced libraries, we have the Flanagan project, and here we have in the integration package, we have integral function, which is pretty much a functional interface that has only one public abstract method called double, and it's a function and its parameter is a real double value function, and it returns a double value for the function. I mean, I wouldn't call it the method function, maybe the method value. So in our integral project, when we define the integral function 1D, we call it as value, which is I guess in my opinion it's a better name instead of having function as the name, okay? So and then in the integration class, and so let's quickly have a look at what method it has. It has a set limit, set lower limit, set lower limit, set upper limit, set Gauss-Legendre points, and set number of intervals, get integral sum, get integral mean, get integral standard deviation, get Gauss quad distances, get Gauss quad weights, Gauss quad. So it has a method Gauss quad for doing the Gauss quadrature, Gauss-Legendre quadrature integration, Gauss quad with the parameter of int, which I assume is the number of points, and then some static methods for Gauss quad, Gauss quad coef, trapezium. This is the trapezoid method. Trapezium, get trapezium intervals. Backward, this is backward rectangle approximation. Forward, this is forward rectangle approximation, and that's it. So it doesn't have some of the methods that we implemented, like Simpson or center approximation, center rectangle approximation. So it's mostly based on the Gauss quad and trapezoid. And again, when we discussed Richardson extrapolation, we said that you can in fact take any of these and put it on steroid by applying the Richardson extrapolation, which increases the rate of convergence. All right, so let's look more into the details of this class. So the class called integration, it has obviously an integral function which is initialized to null, has a Boolean set function, lower limit of the integration and upper limit, set limits false, Gauss-Legendre points. The default number of points for Gauss-Legendre is 0 points. Set Gauss-Legendre points, number of intervals, the default is 0. Set intervals, it's false. Integral sum is by default 0. Integral mean, integral standard deviation, and integration done, integration stats done, array list of integers, Gauss quad index. So it has an array list for Gauss quad index, array list of double, Gauss quad distance array list, Gauss quad distances, Gauss quad weight array list. So these are the weights. Gauss quad weight. So I guess the distances are just the roots of those points, the quadrature points. Gauss quad weights, Gauss-Legendre precision. So the default precision is 3 times 10 to the negative 11. Required accuracy default is 0. Trapezium accuracy is 0 by default. Trap accuracy, which is a static variable, and I guess this is going to be used in the static trapezoid method, because I guess the good thing that this guy has done is that for any instance method like Gauss quad or trapezoid, it also has defined a static variation. So you just call the class itself and pass in your integral function. For example, here's the static version of the trapezium, and you pass in your integral function, and then var1, var3, var5, var7. I assume that these are just the bounds of integration and some of the accuracy error, and then probably int is the number of subintervals or something like that. That's a good approach to have for any instance method. You also define a static variation, a static version of it. All right. The default number of intervals for trapezium or the trapezoid method is 1. All right. And it has a no-R constructor, public integration. Once you have a no-R constructor, obviously you have to add the setters and getters for all the parameters that you need. That's why all of these are set integral functions, set limits, var1, var3, lower limit, upper limit, set lower limit, and it also has flags for making sure that the limits have been set. So there's a set limits flag here, set lower limits, and then so it assigns the lower limit and checks the upper limit if it's nan, because the default for the limits are nan. If it's not nan, it means that the upper limit has also been set, so it changes the set limits flag to true. And then set upper limit, set lower limit, set upper limit. Yeah, these two seem to be exactly the same, so I assume this is a bug in the decompilation of the class. Yeah, similarly for the upper limit, it assigns the upper limit and then checks the lower limit. If the lower limit is not nan, it means the lower limit has also been set, so it changes the set limits flag to true. Set Gauss-Legendre points, how many points we want for the Gauss-Legendre integration. In our implementation, we actually implemented for the Gauss-Legendre 2 default versions, 3 point and 5 points, and we said that 5 points is typically enough, and instead of increasing the number of points for the Gauss-Legendre, we divided the entire interval into some sub-intervals like 100, and then we performed 5-point Gauss-Legendre over each smaller sub-interval, and that's a faster approach in my opinion. Than it's definitely a faster approach than increasing the number of Gauss-Legendre points. But you can specify, if you are going to do Gauss-Legendre quadrature integration, you can specify how many points you want for Gauss-Legendre. And again, remember that this class, this implementation, doesn't break the interval into sub-intervals. So if you have a big interval, then you have to increase the number of points in order to get a good approximation. Set number of intervals, okay. I guess that the number of intervals is used for trapezoid. Let's go here. So the first occurrence of the number of intervals is here. Yes, it's in the trapezoid method. So it does, for Gauss-Legendre integration, it doesn't divide the interval, but you can set the number of points that you want, the number of quadrature points that you want for Gauss-Legendre integration. Set number of intervals, get integral sum, which just returns the integral sum. Okay. Obviously, it checks the flag for integration done. And if the integration is not done, it throws an illegal argument exception and says that no integration has been performed yet. And then another getter for get integral mean, the mean value of the integral, get integral standard deviation, and then there's an array, get Gauss-Legendre Gauss quadrature distances. These are the quadrature points. Gauss quad weights, these are the quadrature weights, Gauss quadrature, Gauss-Legendre weights. All right, so the distances here means the quadrature points. I call them quadrature points. And then it has the main Gauss quad method for performing Gauss quadrature integration, which takes no argument. So here it assumes that you have already set the number of Gauss-Legendre points. That's why right away it checks the set Gauss-Legendre points. And I'm assuming this was a flag. Yes, set Gauss-Legendre points a flag. When it by default it's false, it means the number of Gauss-Legendre points has not been set. Now the problem here is that if you set it and then you change the number of points, then yeah, it still sets the flag to true, so there's no problem there. So if you haven't set the Gauss-Legendre, the number of Gauss-Legendre points, then it throws an exception, number of points not set. Else if the limits is not set, it throws a new illegal argument exception, one limit or both limits not set. If the integral function is not set, it throws a new illegal argument exception, no integral function has been set. And if all of these are satisfied, and then it sets the creates an array. Gauss quad distance is basically the quadrature points, and then an array for quadrature weights, and then var1 true, var2 -1. Gauss quad index is empty. So what was this one? This was an array of an array list of Gauss quadrature in integer, array list of integers. For var3 equals 0, var3 less than Gauss quad index dot size, var3 plus plus integer. This go get var3. var4 equals this Gauss-Legendre points. So basically what happens here, and then var1, var1 is false, var2 equal 3, so it has a flag var1, and then Gauss quad index, Gauss quad distance array list, again weights. Again, these are all for getting the yeah, these are just for getting the weights, calculating the weights and quadrature points. So let me see where this happens. So the Gauss quad index is initially empty. Okay, and then integer this Gauss-Legendre points. Okay, Gauss quad list, double this Gauss quad distance array list and weight array list, and it returns a okay. So this is all for calculating the Gauss quadrature points and weights, and here's where the actual integration happens, which is just a summation, right? But you have to be careful about the scaling. So here this is 0, half of the upper limit, lower limit over 2. var 7 is upper limit minus lower limit over 2. And again, in order to refresh your memory what these scalings are, I'm going to go back to the when we looked at the Gauss-Legendre, and we said that Gauss quadrature method is only defined based on the Legendre polynomials over the -1 to 1 interval. So if I want to calculate from A to B, I have to do a mapping to map this integral to -1 to 1. All right, and then the coefficients of this mapping are upper limit minus lower limit divided by 2, upper limit plus lower limit divided by 2. Okay, and then here, so my new function that actually goes into the -1 to 1 to integral if the original function b minus a over 2 times x plus b plus a over 2, and here x is between -1 to 1. So I calculate this new g of x using the Gauss-Legendre. So basically this integral becomes sigma of I from 1 to n wi g of xi, and xi are quadrature points which are between -1 to 1, and wi's are quadrature weights. And then when I calculate this, I have to scale it again, b minus a over 2. And also I mentioned that this is where obviously we see that the error of the integration also scales linearly with the length of the interval. That's why if we are integrating over a larger interval, we have to have a better have to have a smaller error. So that's why we need to increase the number of points, quadrature points, as we increase the size of the interval. Otherwise, then the error gets also scaled with this factor, and that's not good. All right. So here are the two coefficients, half of the upper limit plus lower limit, half of the upper limit minus lower limit. And I assume var 9 is basically one of these two is keeps track of the integral. So var 11 0, number of Gauss-Legendre points plus plus. Remember, we need to multiply the weight. Okay. So var 7 is the scaling factor, upper limit minus lower limit over 2 times Gauss quad distance, and so this is basically scaling the quadrature points. Remember the mapping, it was b minus a over 2, this var 7 times the quadrature point, and plus this var 5, right? So this multiplies that creates var 9 Gauss quad weight times this integral function var 5, which is the b plus a over 2 plus var 9, which is b minus a over 2 times the quadrature point. Okay, so this calculates the integral function at the so basically it calculates the integral function at b minus a over 2 times the quadrature point plus b plus a over 2, and does the summation for all the number of quadrature points. And when it calculates the sum, then it multiplies by this scaling factor b minus a. Again, var 7 is b minus a over 2. All right, and then integration done, it sets the integral sum and then returns the integral sum. All right, so the only thing here is how it calculates the quadrature points, quadrature distance, and quadrature weight. Obviously this is a more efficient way of doing it, and you can look it up on Google or on the algorithms to actually do to find the quadrature points and quadrature weights. The way I did it, I just simply said that okay, these are the roots of the quadrature points are roots of the Legendre polynomial, and quadrature weights are related to the derivative of the Legendre polynomial. So I calculated them that way, which is not a very efficient way, obviously, especially if the degree of the Legendre polynomial is very large. So this is a better way of doing it, okay? All right, so, and it has another method, Gauss-Quad, with a parameter, integer parameter, which defines the number of Gauss-Legendre points, right? So if you call this and pass in some integer, it sets the Gauss-Legendre points to this parameter, set Gauss-Legendre points, this flag to true, and then calls the Gauss-Quad with no argument. And it also has a static method for Gauss-Quad, integral function, double var1, var3, which are the limits of the integration, upper limit, lower limit, and then the integer var5 is the number of Gauss-Legendre points. So it creates a class integration and calls one of the constructors, which takes the integral function, lower limit, upper limit, and then calls this on this class calls the Gauss-Quad method, which takes the number of Gauss-Legendre points and returns the result. And then it has another method for doing the integration, but it returns an array list of double values, and it returns the Gauss-Quad integration plus the mean value of the integration and the standard deviation. And again, I'm not going to go into the details of how the what is the standard deviation of the integral. But there are approximate equations that you can again search for them on Google to see how we can define the estimated error, which is basically the standard deviation, and then for the Gauss-Quadrature method. And we have also a static version of this method, and then Gauss-Quad coefficients. So this public method basically returns the Gauss-Quadrature coefficients, and then so these are based on the Legendre polynomials, and again this is a relatively efficient algorithm for calculating the Gauss-Quad coefficients, the quadrature points and weights. And in this class, the quadrature points are called quadrature distances, and the weights are called quadrature weights. So you can just use this one to just calculate the basically this doesn't return anything, it's a void function, and it just populates the Gauss-Quad distances and Gauss-Quadrature weights. And then we also have a static version of that. So you pass in two arrays and the number, and then it populates the Gauss-Quadrature points, Gauss-Quadrature weights, and I assume int here is the number of Gauss-Legendre points, right? So it creates an integration object and then sets the Gauss-Quad coef var2. So it's basically here, int var1 is the number of points, and then var0 is get Gauss-Quad distances. So you can invoke this method to get the quadrature points. var1 is var3 Gauss-Quadrature weights. So this returns the Gauss-Quadrature weights. That's it. So again, for Gauss-Quadrature integration, all we need to do, we need to get the weights and the quadrature points. Once we have them, we have to take the quadrature points, which are always between minus 1 to 1, and map them to a point using this mapping that is between a and b, because the integral function is going to calculate at those points, okay? And once we do that, we calculate this sum, and again we have to scale it back from b minus a over 2 to find the correct value for the integral. And again, because of this scaling factor b minus a over 2, the error of the Gauss-Quad also linearly scales up with this factor, which is not good at all when the interval is very large, or b minus a over 2 is a large factor. That's why you need to reduce the original error by increasing the number of Gauss-Legendre points. So the next one is the trapezoid method, which is pretty simple. Trapezoid is breaks the interval into some number of sub-intervals, right? set intervals is basically the flag for making sure the number of subintervals is set. And then integral function, it evaluates at the point. Integral sum plus equals half of the initial point plus the end point. And then it just adds them up and then returns the integral sum. And if we call the trapezoid method with some integer parameter, it just sets the number of subintervals to this parameter. We also have a static version of the trapezoid method. And then we have a trapezoid method based on the required accuracy and then the number of subintervals or max subintervals. So this is more like an adaptive approach. You set the accuracy and the max number of subintervals. And I assumed it starts with some low number of subintervals and increases the number of subintervals. And with some increment, and then checks when the accuracy is reached. So this is one way of doing that. We have a static version here. Get trapezium intervals. This just returns the intervals accuracy. This is the rectangle backward integration, right? It just takes the value of the function times the length of the subinterval, and then backward with some integer parameter, which is the number of subintervals. A static version of the backward. Forward, I'm surprised that it doesn't have the center approximation. So again, for forward, you calculate the function at the beginning of each subinterval multiplied by the length of the subinterval, which is again uniform partitioning. For rectangle approximation, we always assume uniform partitioning, upper limit minus lower limit divided by the number of subintervals, and we have static versions of those. Yeah, so this is a very good class. It doesn't have the Simpson method, but it has very good and I assume very fast Gauss quadrature approach, and the trapezoid and forward and backward integration. So I highly recommend you to use this class also whenever you can, and it's in the Flanagan library in the integration package. So you first define your integration function as a functional interface and then pass it to the integration class. I hope you enjoyed this video, and I'll see you in the next one.